Just kind of going over the agenda yesterday, as you recall, we went through our history, we went through all the different types of permits, recent permit policy shifts. Then we got into the kind of the heart of the matter with federal NSR applicability. We went through some definitions of emission sources, and we went through our one thing you need to know, which is the definition of major modification, and how there's 26 things embedded in that definition of major modification. And then we went into replacement, restarting, debottlenecking, aggregation, and said if all the stars lined up, those things would be treated as existing units rather than new units. Then we went into excruciating detail on the project accounting, or what we're calling step one, emission increases, significant emission increase, and how to determine that. And within that, we talked about the concepts of the baseline actual, the projected actual that came out of the NSR Reform Act. And then we talked probably in as much detail as you ever want to know about able to accommodate, and how to use those concepts in your permit review such that you decrease that project increase to be only the amount that is caused by your project, right? Then we said, okay, if you're over that significant emission rate, after all that, you got to go through contemporaneous netting, and we went through contemporaneous netting and talked about the new policy that says you've got to use PTE to baseline actuals for all your projects in your contemporaneous window, and how ridiculously absurd I thought that was, but it's what TCQ is doing because EPA wants them to. And then we kind of put it all together in this stepwise approach. It was, for step one, we had A, B, C, D, E, F type steps to go through to kind of put all these concepts in order in a guide you could hopefully take back and use, even though it's a pretty simple guide. You could use it as you evaluate your management of change and all that. We then went through a crazy permit strategy where it might have been actually better to take a PSD review just to keep that second project out of the contemporaneous window. Talked about start of construction a little bit, and then ran out of time. So we're probably going to go back and pick up the BACT now, and then we'll get on to day two. We're making a fundamental shift and to try to avoid PSD and telling you how to do all that through the project accounting step one and the contemporaneous netting step two. Now Bruce is going to throw up his hands and say, I surrender. We triggered PSD. Now what's ahead of us? And that's mainly going to be BACT and modeling to some extent. And Title V and ended up with our movie presentation, Great Moments in NSR History. Okay, so that's pretty much where we are. Let me pull up day one again and hand this over to Bruce to talk about BACT. And you might want to mic up there, Bruce.
Yeah.
You want to throw this?
Good morning. How's everybody doing? Well, we had, like Randy said, we had a good day yesterday, and the whole theme yesterday is staying under those thresholds so we could do a minor source permit rather than a major source permit, an NSR permit. Whether you're in the attainment area or non-attainment area, whether you're pollutants or attainment pollutants or not. So, like Ray said today, we're going to concentrate on, okay, we went through all those steps, we used every trick in the book, we used all the netting, all that could have accommodated, we built a demand growth, we put everything in, we shortened our bar for emissions from this to this, but this was still 42 tons or 50 tons. Or frankly, we started with 800 tons, so there's not much we could do. We could reduce it to 100 tons, but it's still way over. It's always going to be a major project. I have a client who has a lot of reduced sulfur compounds, and the threshold for that is 10 tons. their average emissions are 1,200 tons. Okay, well, what percent of your operation do you have to change to stay under 10 tons when your emissions are 1,200 tons? 2%. You can't turn around without tripping PSD every time. No matter what you do, it's going to come out above. So we're going to spend the next day and a half or so talking about, okay, now that you're in the program, what does that mean? What's the best way to get through this process with the least issues and expedited? Time is always against you on this part. Your project team always wants the permit tomorrow. Once you trip PSD, you're in for a long review time period at the agency. You're into some of these analysis take a long time to do. And especially on the modeling thing that can drag things out, Randy's going to give a lot of hints on stepwise procedures to try to optimize and find the right way through that permitting, that modeling path, so you don't slow down everything and basically, not allow the project to be done because the modeling won't pass. So he'll give you lots and lots of hints on that today. We're going to start out though with a little bit on the BACT program. First of all, I think requirements you can't avoid, you've given up. So PSD, the main two elements of that are BACT and the impact assessment modeling. So the BACT was originally put in as a technology, not as the emission rate or anything, any specific rate, but just say you have to use the technology for control that everybody else basically is already using, and it's available and it's proven to work, and that's our least expectation, that you do what everybody else is already doing, works at the best level. The impact assessment modeling basically say you're all of a sudden now you're emitting a major amount of pollutant. What's the effect on the ambient air? Are you going to violate an ambient air quality standard as a result of your project? Are you going to use up the increment that's left in our clean area, use up too much of the increment so you don't pass the modeling? So it's a balancing of the control technology on one side and making sure the ambient air is clean enough in this clean PSD area, attainment area. And if those two things are balanced, the project should be viable and the public should accept it and everybody should be happy. There's all kinds of other impacts we'll talk about that gets thrown in for good measure, even though the first two, the BACT and the impact modeling, are really the things that can make or break the project. For non-attainment new source review, they up the ante on both on the control technology. So now instead of just being the best available control technology, we want something that's out there already, has been proven. You can't argue that it's not applicable because it's already been used for your particular source. For non-attainment new source review, they up it to LAIR, or lowest achievable emission rate. And whereas BACT, the big factor you get to count cost in that is the cost-effective control. On LAIR technology, it's the lowest rate that anybody's ever produced anywhere in the world, regardless of cost. And you have to almost force fit it to your process if it's any way applicable to it. So it can be very, very expensive as a result, and even almost experimental at some level, to try to use these control strategies to control your system. Every once in a while, LAIR and BACT to be the same thing because no one's done any better than what's done right now. But a lot of times, somebody in California has put on some weird unit, some weird control that costs 10 times as much, and used it once, and now it becomes LAIR, and you get stuck with it. We'll talk more about that when we talk about non-attainment new source review. And the other thing is, since you're in a non-attainment area, you don't model to see if you attain the standard. You're already over the standard. The air quality is already a standard for the existing sources. So anything you do makes it worse. So what you have to do instead is, to keep it from getting worse, you actually have to reduce your emissions by more than what you emit, and that's what the offsets are all about. So you actually have to buy offsets from somebody else to cover your emission, so there's a net reduction in the air shed as a result. And we'll have a good speaker on Thursday come in and talk all about that negotiation part and how that works and how, what the main things to look at if you get in that situation where you're required to buy offsets. So we'll talk about all these before filing the needs for the new source review permit, because any one of these can kill the deal. If you can't install BACT, if it's too expensive, it raises the price of the project too much for the project to be viable, then the project won't go. We'll see, especially in the modeling, this is an iterative process though. If you wind up tripping BACT, you didn't think you were going to, but you were just over that threshold, you can't go get lower. You put on controls, hey, those controls lower it by a factor of 10, because it's 90% control. Now all of a sudden you got only 10% of the emissions and you don't trip the threshold anymore. You're putting on controls you didn't expect to, and now your emissions are 10 times lower. Maybe you don't have to do PSD now, but you do have to do the BACT controls. So you put those on voluntarily instead of as the requirement. You get out of PSD, you still have the controls, but you save a lot of time by doing a minor source permit rather than an NSR permit. Same with modeling. You might model and you determine, hey, we got to reduce the emissions from this particular boiler, this particular heater in order to pass modeling. That reduction is just enough to get you out of PSD to begin with. So as we go through all these things, keep that step in mind that every time we do something to reduce the emissions, go back, try that analysis again. Was that incorporated in the initial analysis, yes or no? If it wasn't, go back, see if your netting analysis and everything works out that you don't have to do PSD anymore. You'll still have to do the controls, but on a voluntary basis rather than on a mandatory basis. Okay, so that's Harrison Ford giving up. PSD, why, we always assume that we want to avoid PSD. Why we want to avoid PSD? We want to avoid PSD because all these things we have to do, and mainly this first one is the 1 year review time is typical. It's most states won't promise anything faster than 1 year to process a PSD application. People have gotten them faster. Other ones have taken years and years to get through. I think the fastest one I ever got was like 7 months, and that's because it was really small. One of these small projects is just tripped over, and it was exactly the same as they'd done before, and it was kind of a sequential project, so it went pretty quick. But even that took 7 months to get through the agency after the application was all the modeling was done, all the BACT was done, submitted, and then in for review. Part of that is administrative steps that they have to do, their own clearance. It's getting worse all the time because every agency is in the fear of lawsuits from outside parties, so they try to make their analysis and their statement of basis for the permit as bulletproof as they can, because they know that as slow as they do, it's going to be even slower if the lawyers get involved and you have hearings and responses to comments and all that kind of stuff going on. It can drag out even longer. But once you do, besides the 1 year time frame, which nobody wants to wait that long to do a project if they can avoid it, most minor source permits take between 60 and 90 days. A lot of states have those kind of drop dead dates. If they don't get back to you in 60 days, it's approved. And so it's much quicker than waiting a year or more for a permit. The emissions evaluation, it's pretty much done for everything, for minor source permit as well, regulatory applicability determination. But the BACT and the impact assessment are really the two big things that get added on. And we'll talk about the 5-step top-down process that the feds have, and a little bit about how Texas allows a different process. And this economic reasonableness is the real big factor that distinguishes it from LAIR and from other kinds of technology review. Other impacts, other considerations, and then of course the public and federal review. That's another big thing. A lot of state programs don't require federal review or even public review unless they're over certain thresholds. You can get a permit just by dealing with the agency and not have to have hearings, not have to have a public comment period. PSD permits, non-attainment new source review permits always have federal review and public comment periods associated with them. So that's part of the thing that adds or is part of this 1-year time period to actually process an application. And how many have gone through public hearings before with their permits? Anybody? Yeah, how much does that drag out things? A lot, because you have to go through another iteration of comments. Sometimes the agency, depending how tough they are on their own people, they go back and change something in the permit. You gotta go back and accept that. You have to do something else to respond to the comments. It can drag out, even on one cycle of hearings, let alone 2 or 3 cycles. So we said it takes a year. Well, some permits have taken 3 or more years to get done. I know a paper plant that waited 5 years to get an application. They had 4 simultaneous PSD permits in the agency at a time, waiting for them to be approved in sequence because they took so long to do. They kind of loaded up the agency. But anyway, this is a good decision. It says after 3 years, Avenel sued EPA under the provisions of the Clean Air Act, and basically continue to require Avenel to address new requirements more than 1 year after the complete application was filed. And the Clean Air Act actually says that the agency must, act within 1 year. And so they took him to task on that, and the judge says, yes, you must take final action within 3 months, which they did, sort of, by grandfathering the 1-hour NO2 and SO2 NACs and greenhouse gas permitting issues into their permit to resolve the issue they were taking so long to resolve. That whole decision is in your jump drive as well. I think we got one more process here. Like I said, it's entertaining reading. This is one of Randy's favorite quotes, I think. It says, in essence, EPA contends Congress's statutory mandate is subservient to EPA's regulatory review process, and as such, this court has no authority to require the administrator to comply with this statutory requirement. How absurd. Clean Air Act says 1 year, and they're saying, well, EPA's got other concerns. It might take us more than 1 year, or, we don't really have to do what Congress or the courts say. And the courts, of course, didn't like hearing that, and they came back and slammed them with how absurd. And it's like, it's axiomatic that the act of Congress is the patently clear and unambiguous, such as this requirement in the Clean Air Act, cannot be overridden by a regulatory process created for the convenience of the administrator, no matter how much notice and comment precedes its creation. Simply put, that dog won't hunt. So that's some of the more colorful language that's ever been in court rulings, I think. And they even go further to say that EPA has labored mightily to convince the court that the temporal requirement enacted by Congress is somehow ambiguous, and therefore this court should defer to the EPA's interpretation. Horse feathers. The EPA's self-serving misrepresentation of Congress's mandate is too clever by half, an obvious effort to protect its regulatory process at the expense of Congress's clear intention. So talk about getting snapped back from that requirement. So
You gotta love those southern judges.
yeah, the southern judges. So basically, the result of this is that all the agencies, all the state agencies are on notice that they have 1 year to process your PSD application because of this.
After completeness.
After completeness review, and that's the trick, is that it may take them a year to give you a completeness review and going back, or they just don't give you a completeness review to lock them into this, to lock them into this time period. Yeah, we left some of the books out from yesterday's stuff. So we kind of feel this way after reviews.
I want you to get up now. I want all of you to get up out of your chairs. I want you to get up right now and go to the window, open it, and stick your head out and yell, I'm as bad as hell, and I'm not going to take this anymore.
So by about month 11, and the agency's still stalling out on your permit, that's the time to pull this movie clip for them. So we can start. Maybe before we get started, we had some new people come in today. Why don't you introduce yourselves to the group and go around? Debbie?
With Formosa Plastics Corporation, and I'm our corporate air permits manager. I'm out of Delaware. I live in Delaware, but I work for the Texas plant in Point Comfort, Texas.
Okay, cool.
I'm Matt Ernest. I'm with Sage.
Hey, Matt.
Previously with the TCQ.
Okay, cool. And in the back. Sit back. Both of them.
I'm Josh Baker. I'm with Brown and Gay Engineers out in Frisco, Texas. I'm an environmental science fan. Spent the last year or so developing a permitting group with us.
Cool.
My name
Fine.
is Brett Hanson. I'm the environmental manager for S&F Holding Company, which manufactures water treatment chemicals throughout the world.
Great. Well, we're going to, first step, we said that one of the toughest new things about once you trip PSD, you got to go through BACT. And it's also a good thing to kind of think of first when you trip PSD because it might have consequences on what your final emissions are going to be in this project. You might go into the project and all our netting analysis and everything we did yesterday assumes some kind of emission levels were assumed in that, right? How big was the boiler? What controls were on the boiler? How much emissions did it emit? And that was all worked into our analysis. Well, if you do a BACT and it changes that assumption of what the controls have to be or what that emission rate has to be from the boiler, it has a trickle-down effect to all the calculations, everything we did yesterday. We might have to go back and redo that whole thing. And who knows, we might get lucky and say, even though we tripped it one way, if we put a little bit more controls on, we'll get back out of it again. So it's definitely good to do this before you launch full into the modeling, full into all the other analysis, to see if you were kind of in the right place on your controls, on your initial assumptions. So BACT defines the emission limitation based on the maximum degree of reduction for each pollutant, which the agency, on a case-by-case basis, taking into account energy, environmental, economic impacts, determines is achievable. So our movie quote here is for a few dollars more. So if you spend a few dollars more, what more control do you get? If you spend a few dollars more, what control do you get? So you're measuring controls versus costs, economic impacts, environmental impacts, energy impacts. So you can always, like I said, go all the way to layer technology, lowest achievable emission rate, but it might not be economical, it might have environmental effects, you might be creating another pollutant, you might be doing lots of things, and BACT takes those all into account and tries to balance those effects against the level of control that's expected. So for that, new major source shall apply BACT for each regulated NSR pollutant that would have potential emit in significant amounts. So all that netting and everything we did yesterday, just come up with which ones have significant amounts. We use that to determine which ones have to apply BACT. So if you're not major for a pollutant, you don't have to apply BACT for it. If you don't make a physical modification for a emission unit, you don't have to do BACT for it, okay? So we had affected units like the boilers that didn't have any modification to them, but yet we had to include those increases in the emissions and the demand for the steam, you might say, in the calculation for our netting. It wasn't a modified unit. It doesn't fall under the BACT. So those are two things. One, it has to be a pollutant that goes over the significant amounts, and two, it has to be actually a modified unit for the BACT to apply.
Yeah, and we're talking about federal back now.
Right. Federal BACT. All these things are these are all, some states have their own BACT program, and so they have their own rules associated with what's included and what's not included in that BACT analysis.
In Texas, everything goes to
Yep.
at least the state back.
So BACT applies to PSD major source permitting, may apply to minor source permitting, Randy just mentioned, cannot be less than any federal regulation. So even though it balances the cost effectiveness, you might have a RACT rule already in the books, you don't think it's cost effective, but that's too bad, it's already on the books. That's the minimum of what the control has to be. There's already rules that says NOx has to be 0.02, it has to be 0.02, you can't go any higher than that and call it BACT if the rule says it has to be 0.02. Practically cannot be less than any state regulation. it's not written into the federal rule that it has to be greater than a state, but trying to prove that your best available is best, and there's a state rule that everybody else is doing is a better control, isn't a valid argument, basically. And the BACT must be practically enforceable, which means there has to be a method of compliance included with your analysis, and the monitoring requirements consistent with the averaging limit. So if you set a standard at a pound per hour, you have an hourly way to monitor. If it's related to production levels, then you have to measure the production levels as a result. So you have to find some way to make whatever limit you come up with enforceable in practice. Before we get in the process, the other thing is it has to actually be, well, it comes up a little bit later, it has to be demonstrated. It has to be something that's actually been out there, has been used. Your agency guy can say, yeah, I once heard that you could probably use a cryogenic system and blah, 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 and it would work just fine. Says, well, have anybody actually tried it? Yeah, they tried it. Did it work? No, it didn't work for them, but it should work for you. No, if it hasn't been demonstrated, it's not available, and that'd be a part of the word, available. So it has to be achievable, has to be available, has to be proven to have worked with somebody before to really be the baseline for BACT.
Okay, so how do you, somebody can put something in his back and it makes it to the clearinghouse. I can make anything up. And it gets put in the clearinghouse. How
Right.
do you go back and find out if what they said they could do, because a lot of that's just crap.
Right. Well,
For lack of a better term, I mean, there's no way they can do it.
I agree with you. I always feel like I'm just checking a box going through the clearinghouse. And it's really more recent permit reviews, what's recently been issued by your agency. And
So do you cut, is it
just a website guidance in Texas for Tier 1.
Is it rude to call the company and say, you said you can do this, can you really do it? Come on, tell me.
And why did you do it? Did you do it because of BACT, or did you do past impact modeling? I agree with you. It's really messed up.
generally, we call the source to see if their control equipment they bought performs the way it was supposed to before we called the company who made the control equipment and asked them if it performed the way it was supposed to. Because you get two different answers sometimes. But anything in the BACT, you do have to kind of research that next step. Just, they put it in the BACT, is it still in their permit? Maybe the next permit, they took it back out because it didn't work and they put a different control in.
Did they go back and remove those from the clearinghouse?
Not necessarily.
Yeah, or they get a permit, but they never build it.
Right,
That
right.
happens a lot.
Oh,
Yeah.
yeah, that's that Arizona Clean Fuels.
Yeah.
So, okay.
So checking the permits, how they actually got issued and whether there's any follow-up from those same permits is kind of our first step usually. Quizzing the actual source, like these guys put in biofiltration for this VOC source. And does it work? Well, it works about 40% of the time if logs levels don't get this. So you find out all the qualifiers for it that you can use in your analysis to see if they're appropriate or not, even though the BACT maybe not mention all those qualifiers that are in real life are really important.
I've seen recently someone of the back limits will be on an hourly basis and not an annual. Why would they want to do that?
Oh, boy, you're really pushing my buttons.
I mean, that should be based on an annual and they do an hourly. You have to address it, but it's an hourly. You can't.
I try to make it real clear in all my applications that you're talking about performance specifications as a special condition. You're not talking about BACT when you start talking about short-term. But I've largely been unsuccessful. I mean, the whole premise of BACT is dollars per ton control. And a lot of the agencies don't seem to get that. And, I've gone in numerous times and said, look, even your website, let's say for not, says 0.01 pound per million BTU on an annual basis. Well, they want to put a short-term limit in there too and call it that. And going, okay, if you want a performance specification, we can put that in there, but it can't be 0.01, maybe 0.025 or maybe 0.015 with some extension. by, and all this kind of stuff. What you really want to control is that pound per hour that you have in your MERT.
Right,
For a lot of those turn down conditions, you're not gonna get that kind of performance on your prior equipment. And, you know, it's kind of, it's continuous exercise to kind of pull that back and say, no, BACT is an annual number, and short term is a performance specification that you may or may not demand that we put in as part of our special conditions. But
Yeah.
I agree with you, the agency doesn't agree with either one of us, I don't think.
Yeah, Randy and I and others are always fighting the battle of eroding what the BACT is supposed to be for. It's supposed to be a control technology. It's basically say, is it, you do a baghouse, or you do a scrubber, do you do an ESP for particulate control? Which one's appropriate? Well, baghouse, okay. What's appropriate for control for your particular source for the baghouse is whatever it is. But they've changed, that's eroded over the years to not just baghouse, but baghouse at 99.9% control with all these other conditions in it. And that really wasn't the main theme. It was supposed to be pick the control technology that's best, and then use that and apply it to your process. Not pick a emission rate, like lowest achievable emission rate. Layer technology actually says 0.03 pounds per hour is the lowest rate that you can get. So they've kind of morphed the two, and they're even mixing in work practices and other kinds of things into this BACT definition that really, if you look back to where it was created, it wasn't the intent of it.
Do you think some companies may use that as a method to screw the competitors?
Do I? Is there anyone from Dow in the room? I'm just joking. Well, I tell you, whether they intend to do it or not, they do it. And I can't speak to intentions, of course, but, I mean, it does happen. Face it all the time. You know, company XYZ got their permit issued 11 months ago and had this requirement. You should too. Well, I can point to another permit that was issued 12 months ago that didn't have that requirement. And you can't tell me that there was a technology advancement during that 1 month between issuance that really drove that change. So, you know, that's, sometimes I feel like I beat my head against the wall, but, you know, that's why they pay me, just to go in and beat my head against the wall and see if I can get any relief. But so I don't know about the intention, but the effect is that, yes,
But that is the intention of the ACT, to ratchet control technology down.
Agreed.
As more people adopt it, more people are forced to adopt it.
Right. And as new technology is created and is proven, right?
So it will naturally get rougher and rougher, whether that's the intention of the company that's adopting it or not.
Yeah.
It is the intention of the rule.
Right. No, I mean, we saw that with boilers for a long time, where the BACT was way down here and the old NSPS rule was way up here for one time, and they didn't match anymore. So the NSPS almost became meaningless because anybody that put a new boiler in had to do BACT, and that was much lower level than what the RACT rule probably was for the state.
well, what's unclear to me is the reason they accepted that rate. And in the case I was thinking of, it was a short-term, not BACT, but it was a short-term performance specification that they were pushing on the permit that I had employees who were wanting to get that too, and they were calling it BACT, and it was unclear to me why they accepted it. I mean, I don't know if it was BACT.
Why the client accepted it?
Yeah, it was a short-term limit, and I know I do. I mean, they did it so they could pass the 1 hour NO2 max and get under the seal. It didn't have anything to do with BACT. And, you know, unfortunately, everybody that follows now, they feel like they have ammunition for asking for the same thing.
We have we were putting in a new thermal oxidizer, BACT use for that was, a low NOx burner, 0.06 NOx million BTU. Right, yeah, 0.06, and AP 42 is 0.1, and, we can't, when we run it at 1800 degrees, we can't get 0.06. So I called the manufacturer, I'm like, can you make burners that, no, not at that
See, if it's not demonstrated, then again, the intent was to say low NOx burners was the technology, so it's whatever the best you can do with that technology should have been your BACT,
Right.
instead of specifying a specific number for it.
So
Wait, I mean,
That's encroached over the
I
years.
called the state. I called the state and they were like, well, we understand that if you're gonna run it, if you have certain thermal requirements that result in you running it higher temperatures than it's normal rate of operation, and you're gonna get, you just call that a thermal, it's like a thermal factor that's on top of your low NOx rating of 0.06, and it'll account for that additional.
So that's where the
NOx.
condition, they make a special, those like hers is.
I know, like, really?
One
Why
is
did it have it in
1800
there?
degrees.
The other option you always have is just to go through economic evaluation
Yeah.
and just show it's not cost effective.
But it was Johnny Vermillion, he's like, this is what we've been doing for this. I'm like,
So that's really a backdoor way of trying to get a lower level to be established as BACT, in somebody's permit, and then you have this fudge factor you can use to not actually apply it, so.
Well, I think those are two different issues. One is one person trying to, like, one permit setting BACT, and I think that one permit setting BACT is probably a pretty good argument to say just because one person did it.
Yeah. But it's, again, something you have to argue against in your analysis, so. So we're going to talk about the 5-step process here and a little bit about the Texas 3-tiered approach. And a few more states are actually going towards this, kind of combination of approaches where there's some kind of assumption of level going on. And that's what Texas kind of used a common sense approach for that. So keep in mind, we'll have this up here over and over again, the real benchmarking through the file reviews of recently issued permits. So whatever your step-down analysis is, you've controlled everything, the agency is always going to come back to that, we have very similar source and they agreed to this as BACT, so that's our minimum standard for you. If you want to do better than that, fine, but since we already issued this, we already established this as BACT for them, that's what our expectations for you are going to be. And that's what you're going to have to build your argument against one way or another. You should do it the formal process, but keep that in mind always that last permit that got issued that was most similar to yours with BACT is going to fall on your 5-step process someplace, and you got to make sure it lands at least above or at where you wind up. So recent BACT of similar sources established the standard, and the technology used by similar sources assumed to be feasible and cost effective. So the fact that they've been issued and it's been accepted and it's actually being used, clear assumption that it can be used and that it's cost effective if somebody's using it and making money supposedly for what they're doing, and it didn't bankrupt them as a result. So I'm having what she's having on the Harry Met Sally. Expectations. The BACT layer clearinghouse was put together specifically for the purpose of nice, transparent area database that the federal government would keep and maintain to tell everybody what BACT and layer and RAC currently are for a given type of industry, type of process, type of emissions. How well do you think the federal government keeps that up to date, and who QCs it, and all that kind of stuff? Well, anybody that's used it knows there's lots of holes. It's not that current always. I know permanent engineers I deal with in Illinois are always saying, I looked at back, says, yeah, but these 3 permits came out in Nebraska, or these 3 came out in New Hampshire with this kind of source. Like, how do you know that? Well, I have a guy in Nebraska that sends me this stuff. I go, okay, great. You're 3 months ahead of the clearinghouse. If you want us to do that, you got to somehow get that information. So as a result, don't limit your research as we go through these steps to just the BACT layer clearinghouse, but also use other NSR permits, talk to your colleagues, talk to consultants about what they know about and what they've worked on in other projects. Do a little research, technical journals, see what people are pushing as the next best thing. I kind of look at what's the next best thing last year and see if anybody's actually adopted it this year or not. In the permits, so at least I know what the catchphrases are when I'm looking for something. A lot of time the catchphrases, as you know, stuff evolves. It doesn't, brand new things usually don't appear, so some new jargon's used for the same old thing, but it's a new way of, a new slant on it. And you can use that as being a little bit more cutting edge maybe than the old, just calling it a scrubber. Reports, newsletters, those are basically from the trade associations or the professional associations of the industry that you're in. They keep abreast of that stuff pretty good most of the time, like API for the petroleum industry. They obviously have a pulse on what's BACT and LAIR. And then EPA actually has an NSR bulletin board that's a little quicker to respond to people putting stuff on it than the clearinghouse is. But again, that's only as good as what people put on the board. And so it's not a definitive source. You can't say, since it's not on the board, it doesn't count. No, that's just one thing to pick up maybe ideas. So what is the 5 steps for the top-down methodology? Identify all available potential control technologies. And this is identify everything. A rookie mistake on this is saying, well, this won't work. We know it'll fall out in step 4, so I'm not going to list it. No, list everything. Let it have its consequences as you go through the other steps and fall out. List anything and everything that's even remotely feasible for the kind of control you're talking about. I mean, you don't have to put VOC control for a particular control pollutant, but if it's VOC controls, list all the different VOC controls there are basically out there that have any chance of success on this, and identify all the available potential controls first. Then step 2, you can quickly then eliminate the technically infeasible ones. The ones that, you have a flammable VOC, so you can't do anything that blows up when it has flammable compounds go through it. It's not, this type of resin doesn't absorb this type of material, so it's technically infeasible. This technology doesn't work at low concentrations, has no control efficiency at low concentrations, and your airstream is low concentration. Build any and all arguments to eliminate as many of the technically infeasible options as possible, because if it doesn't work, it doesn't work. If you've got no examples of the control technology out there in other permits in the clearinghouse that said this technology was applied to this particular emission source, this vent stream, then you've got a good argument that it doesn't work. It's not feasible. And you get far less argument back from the agency on stuff that's not feasible compared to stuff that maybe is economical or has some kind of energy argument associated with it. So after you eliminate all ones that are technically infeasible, then you rank them from top to bottom, from most efficient to least efficient control for your particular process. And this is just this step 3. Again, don't skip to step 4 and start throwing things out for things. Actually rank them from top to bottom, most efficient to least efficient. Step 4 is evaluate each control and document results, exclude options due to unacceptable energy, environmental, or economic impacts. Again, most people start with the economic impacts because that's kind of more cut and dry, it's more analytic. You figure out what it's going to cost, and if it's $3 million a ton, it probably isn't cost effective. If it's $5 a ton, it is cost effective. So, and the number is somewhere in between. We'll talk about what is too much in a second. But do the economic impact, get a handle on that, so you get the highs and the lows kind of figured out. And then start looking at the energy. There's one option for the same control, one uses a lot more energy than the other. So the one that uses less energy is preferred over the one that uses more energy. More energy is also more cost, so it probably comes in your economic analysis as well. Environmental is another one. Does the control generate waste as a result? If you put a bag house on, it generates waste. If you put in an afterburner, it actually generates a new pollutant, NOx. We had one case where we were controlling barely a major amount. It was like 41 tons of VOC. And it wound up making the source a major source of NOx as a result of putting the afterburner on it. And so it actually made a major source out of something that wasn't major before for NOx as a result of putting the controls on. So that's a good argument that, you don't want to create a new major source in an area that's near non-attainment for NOx by controlling VOC, which wasn't as critical in the area, and had other options for controlling it that didn't create the NOx. So those are kind of environmental arguments. Creating a solid waste that has to be disposed of, other things that can go into that as well. And then finally, the fifth step is that all these evaluations going to help you kind of move the rankings around from most efficient to less efficient. Now you got these economic benefits that come into play. So you kind of have a new ranking, and then you basically select back the most effective option remaining after you exclude things that are clearly economically infeasible, environmentally undesirable, or energy intensive. Sometimes you don't just get one result, you get another ranking of top to bottom of things that work for different controls. And they might have trade-offs on these three parameters too that you'll have to weigh. At that point, pick the one you think is best for your facility and make the argument on these three on why that's acceptable or at least as effective as any of the other options. Okay, seems like an easy process, right? So the first step and the second step are really the tough ones. What's out there, what's been used, making that complete list. And then the rest of these are a little bit more prescriptive. So another option is the TCEQ uses a three-tiered approach. And instead of going through and listing every possible thing in the world as step one, they basically say, if you use state-of-the-art for the process, hey, that's good for us. If you use state-of-the-art, the best that's out there, and it had its own definition, of course, what state-of-the-art is. But if you use state-of-the-art, we're happy with that. If you can't use the state-of-the-art for the whole process, look at the state-of-the-art for the type of stream. Maybe your particular industry hasn't had this come up before in a BACT or hasn't had a control on it. But there's plenty of vent streams that are like yours that have that level of VOC at that concentration. And so look at those state-of-the-art controls for a vent stream of that type. And then third, do the economic analysis on those choices that you have from either state-of-the-art for the process or state-of-the-art for the vent stream, and take that into account in the BACT. And then you propose the BACT based on one of the evaluations of one of these three tiers. So you say, here's the state-of-the-art, that's good for us, we're willing to use it, it's applicable to us, and should be happy to say use says fine. If you have to go the economic analysis, then you say, that's basically almost like the 5-step. You pick a technology, justify it on economic basis, eliminate other things that could be appropriate on economic basis, and then you pitch that to the state in the application. So it's a little less formal, a little less prescriptive on the 5 steps, but you basically get to the same place, an economically feasible solution that's as good as anyone else has out there for the cost. And it's been determined several times to be equivalent to the EPA program, so the environmental groups can't sue you for not doing the BACT right. So this is the case where you instead of just coming up with a conclusion that you're trying to justify like the top down, you're actually making a proposal to the TCEQ and then justifying why that's an appropriate solution. So you're making an offer they can't refuse. Okay, BACT can be type of control, level of control, emission rate, emission control efficiency, even a work practice or emission prevention, or a combination of these. BACT, when it was really written into the original PSD rules, it was really intended just to be a type of control and maybe a level of control associated with it. So you pick a bag house, you pick a ESP over a bag house, you pick a chemically enhanced scrubber over a water scrubber, because one has 99% control and the other one has 90% control. So, but like I said, it's morphed over the years for all the possible choices and all the possible ways to enforce a specific level of control by putting in emission rates or control efficiency determinations on this. So you might have something like bag house with 99% control and effective inspection and maintenance program. So if you don't inspect it and keep it up, the 99% is going to, they found it's going to degrade, and it's not going to really do 99% over the lifetime. So they'll put this second part in where you have to maintain it and prove that you maintain it at that 99% control over the lifetime of the emission source. Who else? Anybody else have any examples of BACTs where we've gotten a combination of stuff as a result? That's a good example. Okay. Randy, anything else you can think of that?
Oh, there's, all kinds of things like design redundancy for sulfur reduction systems or sulfur plants and things like that that are, don't really have anything to do with control except in situations where you need to have shed steps or something for acid gas going to your sulfur conversion unit. So they'll build in, a redundancy type step or some of that kind of stuff. It's really doesn't fit the traditional philosophical
Right.
BACT approach, but there's a lot of things like that. They make sense, and they kind of just over the years have gone into this bigger bucket that we call BACT.
Right. And again, the state will try to push whatever it can, and since they have this rule that you have to comply with, they'll try to throw as much stuff in as possible sometimes. We've got things like you must keep spare parts for the afterburner on site, so you have a minimum time between breakdown and use of it if you're going to bypass it during that time period. Where they actually specify the number of parts, they go, no, we're not going to get a permit violation because we only have 3 flanges instead of 4 in inventory, even if the thing is working. Okay, if we can't repair it during a certain amount of time because we didn't have the right part, that's fine, but not just a violation because we didn't keep the right inventory in there all the time. So you gotta be careful how those things are worded in your permit, so they actually reflect the intent of being able to comply with that level of type and level of control in the end.
As far as combinations, I see a bunch of greenhouse gases, emission rates, and work practices. You've got good combustion practices.
Yeah.
Work practice standard, and they're trying to set greenhouse gas limits on everything. Which, the work practice standards don't mean a whole heck of a lot, it's going to be emission rates and other things like that. But that region ain't pushing that down my throat.
Yeah, greenhouse gases are really struggling to try to keep it to those first 2 bullets. It really comes down to all the other bullets as well. Truss, I don't think you got a chance to introduce yourself to the crowd here.
Oh, I'm sorry. I'm Tadas. I work with Sage. I had some spare time, so I wanted to come see the experts.
So what are the resources to do all these steps? Again, you start with the BACT layer clearinghouse. Keep in mind that gets put in there by the permanent engineers, by the federal government, keeps it up to date as much as they have. So their priorities, their budgets, everything else come into play of how accurate that database is. There's also EPA Air Pollution Control Cost Manual, and this is kind of the starting point for putting together your economic reasonableness spreadsheets. If you've done this a lot, we've got kind of our own version of the spreadsheets with better numbers and better fixes. You also supplement that, obviously, with vendor information, vendor costs, when you get down to the specifics. And especially if you're trying to draw a fine line between picking 2 technologies, or when you've got one specified, the engineers have designed something into your project, and your BACT isn't coming out exactly the same way, that's when you really sharpen down the numbers to try to balance it out to prove your project team correct, that they did pick the right controls. And so they don't have to switch their whole design of the system because of the way the BACT is coming out. So that's a good start. And then again, for greenhouse gases, there's a website that they're trying to keep a little better job of keeping that up to date, and we'll talk about that in a second. So BACT term must be performed for each modified emission unit that emits the subject pollutant that's major, okay? So if you're not major for CO, you don't have to do any BACT for CO if you didn't threshold for CO. If it's not modified, then you don't do a BACT on it for the federal review. You're not required to do those boilers that you never modified. They have some affected emissions. That whole other box of equipment over here that's not even affected by the project, there you don't have to worry about BACT for any existing equipment that's not affected by the project. You don't have to reevaluate every piece of equipment on the site, just the things that have to do with your project. And controls can be analyzed on a full unit or partial system basis. This is kind of a new twist that they figured out, that you're making all these arguments. Well, it's not cost effective to control because we'd have to build such a huge unit to control this. It's such a dilute system. And they go, fine, but what if you just pulled out this little section that's a little higher concentration that goes to the same bend stream before it's diluted? You could control that, couldn't you, cost effectively? And you go, yeah, but that only controls 10 tons out of the 42 tons that make us major. And they say, that's fine. It's still a process of, still a modified unit, still has to go in BACT. If that's cost effective, we expect controls on just that portion of the overall emissions. So they've broken it down even by emission unit basis, not on a whole system basis. So keep that in mind as you're doing your evaluations, that you can't just say for the whole unit it's not cost effective. If it's cost effective for any piece of it that will reduce some of the emissions, they might use that as a BACT argument to have to install controls on just that one piece that is cost effective. What does that mean for your analysis? You have to go through all those scenarios and break down any logical combinations that you could break down to smaller units to demonstrate each one of those is also not cost effective or technologically feasible or energy or environmentally prohibitive. Finally, the BACT technology considered in the analysis that was derived from another permit must have been achieved not just as a permit as issued. And this gets to the point before. Somebody put it in their permit at a new gas turbine at 0.001. They put it in, it didn't deliver. The best it could do was 0.01. And they go back to this, it's in the clearinghouse, they try to run it. They go back, they get their permit changed. That clearinghouse isn't going to go back and take that out necessarily. And so it still might be in the clearinghouse, it still might be in a permit that has it in there, but it's really on you to find out what really works, what's stuck, what really, over the long term, wound up being control. An example besides the turbines is like these biofilters that work to a certain extent, but under very narrow parameters. And your parameters might be slightly different than the parameters where it works great. And that's not always clarified all in the clearinghouse. It might have worked one way, they had to change something, and they actually eliminated half the emissions that went to it to get it to work properly. All those things are follow-up that might not make into the clearinghouse or make it into the original permit for that matter too. So it takes a little work to go and basically ground each one of those assumptions where something shows up in the permit. It sounds too good to be true, it probably is, but it doesn't really work. And it takes a little research sometimes to track that stuff down.
Give an example of affected but unmodified emission units with third bullet.
Like our boiler case where we had the boiler and it had plenty of capacity already, and you built a new unit that had steam demand, and so you had to count those extra emissions from the steam demand in your netting analysis yesterday. Right. But you didn't do anything to the boiler. It ran just fine. It could run at that level anytime it wanted to. If it got cold, it would run higher level. Okay, so that's not a modification. You don't have to do a BACT on the boiler just because that NOx emissions from the boiler were part of that put you over 42 tons. Okay. That's probably a good thing. Obviously, it goes without saying, but I should say it anyway. If you've got 10 things that add up to your 42 tons, anything that puts you over that was modified counts. So even if it was only a 1-ton source, you have to do BACT on it if it was part of that emission rate that put you over. And for big projects, you might have lots of things add up to that threshold amount that puts you over. Anything that's a modified unit that emits that regulated pollutant is fair game for doing BACT on, even if it's a small tank or something else. Okay, don't skip the steps. I've been guilty of this. I like to skip right to step step 4 and do this. None of this stuff is economically reasonable, so I'm not even going to consider it. And it's a good thing to zero in on the technology to make sure what's proposed by the project is what it's going to come out to. But before you put that application in, make sure you go back and do all 5 steps, put all the possible choices, make sure you didn't miss something. One of the least less obvious choices that somehow trickles down to step 5 without being eliminated. So it's good discipline to do all 5 steps, and you need all 5 steps in the application for it to be complete. BACT may be different for different emission units. Like I said, you have multiple units that add towards that NOx source or that VOC total that puts you over. You might have a different BACT result for different units. One might be an afterburner, one might be a flare because of concentrations or something. So you might wind up with different places for different units. And you have to evaluate each one selectively when you do that. So don't just do one thing for one pollutant. Look at the emission unit by emission unit basis to get your BACT complete. And of course, it might be different for different pollutants. You might have obviously a different kind of control for the same airstream. If you're major for both NOx and VOC in an airstream, you might have different BACT for the two. And sometimes that's a challenge to get them to be feasible, having both kinds of controls on the same vent stream. And sometimes your argument is that, you get to choose one. You can't, both aren't feasible to have. We can't have a wet scrubber and a dry filter on the same thing, so you got to choose one or the other. And in this case, NOx is more important than VOC is, or NOx is more important than CO is. And so we're going to choose to control the NOx, and the BACT falls out for feasibility and economic basis on that basis. Okay, and chemical emissions might be included more than one BACT analysis if it's included one or more pollutant. This is the case for like precursors for PM 2.5. You might have to control the NOx as NOx, and you might have to control the as particulate matter. You trip the PM 2.5 threshold. So even though the NOx is in PM at the time it's released, as a precursor, it counts adding to your total, and therefore you have to control other particulate matter on the side, even though in and of itself it wouldn't have tripped the thresholds possibly. Another case is for reduced sulfur compounds. You have some things that are both reduced sulfur compounds and VOC. Some technologies are appropriate only to sulfur compounds. Some are only appropriate to VOC and not the other way around. Fluorides have their own control technology, for example, separate from VOC or particulate matter. So this last one, as they get more and more into the 2.5, it might be more of an issue going forward. But just keep in mind that different pollutant, the same pollutant might have different kinds of controls associated depending on how it's classified as either PM or as a gas when it actually comes out. So since we kind of late study, we're going to zip through these pretty quick here. In your books, you have little examples of just kind of starting points for each kind of different types of emission sources. So for engines, thing to consider is not only the add-on technology, but fuel to reduce VOC or SO2 emissions. Obviously, you can reduce SO2 emissions by controlling the sulfur content of the fuel. Okay, so is that a controlled technology? No, it's not, but it can be used, argued as BACT, using zero sulfur fuel to control your SO2. Obviously, it works, and it's a good practice. Engine tuning to ensure proper combustion. If you're going to put something with a low, especially the low NOx or low emission rate, they'll probably require some kind of maintenance, some kind of tuning as a result to keep it performing at that level. Or you're going to have tests to demonstrate it down the road is the other option. Boilers, similar engine must consider both VOCs and the combustion products. Low NOx burners obviously have been the kind of go-to BACT for a long time now. Selective catalyst reduction, fuel gas recirculation, there's still something that you need to consider. And if they don't wind up on your unit, make sure they fall out nice and clearly in that 5-step process. Identify available fuel sources, liquid gas. There'll be a slide on this in a second, but basically can the agency say, you're going to build a coal-fired boiler? Can they say, well, BACT for a coal-fired boiler is a gas-fired boiler? Okay, because if you trip for sulfur emissions, okay, well, is that a technology for a coal-fired boiler? No, it's a completely different emission unit that you're talking about. And the wings of politics have swing back and forth on whether fuel choices are legitimate things to consider in BACT or not. Lately, it's swung that you can't just change equipment that's fundamental to the project description as part of your BACT. But fuel is something within the realm of the current equipment you need to consider. So if you have like liquid fuels for a heater, and you have your choice between 10 different liquid fuels, you have to pick the one that has the lowest sulfur content, if sulfur is a concern. So that's legit within a given fuel type or within a given type of equipment. But they can't say you're going to build a coal-fired power plant, and instead we're going to require you to put gas turbines in instead. That's a fundamental difference on the whole project economics, how it's designed, infrastructure, everything's affected by that. And that can't be a BACT decision at that point. Any other comments on that, Randy? This is more on the design of the tank. Usually the underlying RACT rule or NESHAP or New Source Performance Standard will tell you whether it's a floating roof or not. And if it is, that's your baseline. You kind of go with it. So the design, technical analysis, but it even gets to things like minimizing roof fittings and things like that can come into the analysis.
I get a quick question on that.
Yeah.
Do you assess drones? I've been hearing rumbling, people being asked to show they're not cost effective. Has anyone seen that?
I'm sorry, Gerard, say that again.
Yeah, the geodesic domes on the
Oh.
even on floaters. I've been asked recently to run some calculations to show that they're not cost effective. I just don't know if other people are getting that same pressure.
I haven't been asked to do that.
Hopefully it doesn't do anything.
Yeah, really the part of the slide is the tank girl on the slide there in case. Loading operations, again, obviously apply both the loading method and the control technology. So here again, the load, how you do it, submerged loading versus non-submerged loading, for example, is not control technology, but it's a method of operation. That one where they've basically said, yeah, that counts as BACT, you know, how you load the tanks. For existing equipment, a lot of time, loading rack is a good example of something that's maybe an unaffected source, unmodified source that's affected by your throughput increase. You're gonna have more loading emissions, but you're not modifying the rack. As soon as you start modifying the rack, then you gotta do BACT for that rack, even if it was existing before, if you're modifying anything to accommodate the extra flow rates and the extra loading capacities. Submerged loading. Process vent backed. This one obviously is the most unique to your process. It's unique by chemical, it's unique by flow, it's unique by batch versus continuous. Especially batch operators don't have a good way to come up with something on this. So this one really, you have to really customize it. You have to look hard. This is the toughest one to research in permits and in the clearinghouse, because there's so many little differences can make such a huge difference on whether it's feasible or not, or whether it's cost effective or not. Everything from concentration, the type of pollutant, the type of control compatible with the type of pollutant. Here, VOC isn't necessarily just VOC. Some things work great for benzene, but don't work for propane at all. Some things work great for hydrocarbons, but you put a ketone on there, it catches fire. So you have to look at the speciation sometimes at one more level down than just the pollutant level, and make that argument in your BACT as well. Fugitive emissions. Is there an add-on control technology for fugitive emissions? Probably not, other than building a dome around your whole facility that's controlled and putting a carbon absorber on the top of it. But there are different levels of controls for different levels of programs. And over the years, we've gotten so many different kinds of fugitive emission programs for the chemical industry, for the SOCME industry, for the refinery industry, for the or whatever industry, and all those have slightly different levels of what's a leak rate, what's the inspection frequency, and all those, as a result, have a different level of control associated with them. And what's happened is that the states now are expecting you to kind of evaluate that. What level of control are you proposing to limit your VOC emissions, if VOC is the regulated pollutant that goes over the threshold? That these are modified units. They're usually the new flanges and pumps are new units, so they qualify as being modified. And you have to look at what control programs is effective. Is it effective to do just 10,000 ppm leak program or no leak program for the type of emission savings you're going to get by instituting an LDAR program? Well, do you have to go all the way down to 50 ppm leak program that you do every month to get 99.999% control? Well, there's some documentation now on the literature on what level of control is expected by what level of program in there, whether it's, what subpart of the reg generates what level of control is expected. Now that's outlined in the preamble to those regulations. And then you kind of rank again the systems like from least effective to most effective, and you say for the level of control we're going to get from these 10 flanges, we're going to do just the no LDAR program. It's not worth it. It's not cost effective for 10 flanges. Building a new half a refinery where you have 100,000 or 1,000,000 flanges, well then maybe you got to go to this level to reduce 150 tons of emissions by putting in the LDAR program, taking credit for that. So Fuse is a new one that they're kind of concentrating on the BACT. Go and rank those different programs, specify the LDAR program that's appropriate for your level of control. So step 4 evaluations, energy. Usually energy isn't something that eliminates something because it's too energy intensive. It's more or less you get two things that are relatively equal in control, and ones might have used more energy than the other, and you can swap the order of them and pick the one that uses the least energy first. Sometimes there's controls like, dust collectors, they have any energy use compared to combustion or something. Even the energy using for driving the flow through the bag house, sometimes an energy cost for the blowers that go through it. So include all this stuff in your analysis and use it again, just kind of to rank it. The environmental sometimes can be a much bigger thing, that choosing between two technology. One has a huge impact on pollutants for like choosing a combustion source versus a non-combustion type of control. Creating combustion creates NOx, creates CO2, sometimes these things are big units that add a lot of NOx and CO2, and those are not good. I mean, they weren't there if you didn't put the controls on, so you don't want to add pollution to your project, and that's a real good argument saying don't want to add more pollutants to my project as a result of just picking this technology over this one. And finally, visibility issues. Depending on the level of control, some are better at controlling particulate matter than others. Some actually like combustion sources actually generate particulate matter at 2.5. If you're in a visibility sensitive area, having a combustion source versus not having one might be an environmental benefit in and of itself that's worth a lot in the consideration of the control level. Then finally, the economic. Here they started trying to cost reasonable per amount of controlled pollutant, dollars per ton. That's kind of the benchmark or what it's based on. Average versus incremental costs. That's basically saying, what's the cost of controlling it pounds per ton versus how much more do I have to spend to get to that next level. You got 10 things in your list left that are feasible, and this one's 99% control and this one's 99.9, and it only costs you another $1 a ton to get to the next one. Okay, if this one's the cheapest and the most cost effective, how much more incremental cost is it to go to the next project? And it's hard to argue against that, small incremental cost to get a big jump in control technology. And that's something, again, you might consider just volunteering for if it's not too much difference, rather than trying to make a big argument that This one's cheaper, because again, it's the the control effectiveness is the ranking, and you're doing the cost effectiveness to eliminate them, not to reshuffle them necessarily. The EPA control cost manual has a lot of assumptions and a lot of build-up for things like the engineering design costs and assumptions to make on how much plumbing you have to do with certain control technologies to include those costs. All the assumptions in there, you should have your own justification for them as far as what your labor costs are for your market, for example. Assumptions need to be current. There's cost of money calculations in there. If you went back to when this was first in, it was probably something like 14% interest rate or something. Well, that's not 14% interest rate anymore for a cost of money. Much as I like to put that in there to justify something's way too expensive, it's not going to fly anymore with interest rates at 3% or something for big projects. And then there's also state-specific programs. Michigan, for example, has this program where the increased cost of the final product would increase to a level that the project would no longer be feasible. Now, most states don't let you go that far, and to look at your product costs as justification, it's just the cost of actually the control per unit of emissions, so your operational costs. It doesn't matter how much the product's going to cost as a result of your thing. But Michigan being Detroit being automobiles, they've specifically said that, if this control is going to raise the cost of the automobile by $6,000 and therefore it doesn't make the car viable anymore, you get to use that in your argument, in your economic argument, okay? And of course, they've leveraged that, trickle down to every possible product, passing on those control costs into the product costs and using that as part of the economic analysis when they don't like a certain control. But I wouldn't try using this too many other places other than Michigan right now. But definitely look at your state programs and see if they have any specific guidance where they've drawn some brighter lines than the federal government.
So what did they say would increase the cost of how much do they put of How can they make that justification for Michigan for automobiles when they've been saying stuff for automobiles and safety concerns for 40 years?
Yeah.
So what did they say? What was going to increase and how much was the cost going to?
Well, those are still case-by-case analysis, but it snuck into the argument, and that's basically the point I was trying to get across, that that if it increases the cost of the product you're making, that's an economic factor that can be used in the BACT.
So apparently the Highway Safety Administration doesn't have those.
Same concerns, no.
Along that same point, what I've had, this is specific to greenhouse gases, is they're not concerned with the dollar per ton value, but if you show that something like carbon capture sequestration would triple the cost of the project itself, then they say, okay, there, you prove it's not cost effective.
Yeah.
So the dollar per ton argument honestly doesn't even exist. But if you show it's 3 times the cost of the project, then it's good.
And
We're gonna talk about greenhouse gases next, BACT, but yeah, it's crazy stuff. Who builds a 66% margin in your project to triple the cost for carbon capture?
And they tried putting that into, some states tried to wiggle in a BACT review based on the cost of your project too. That's saying it's economically feasible if it's less than 6% of your cost or something, some arbitrary number. And that got beaten down basically by saying it's not part of the 5-step process. It's, what's the cost effectiveness of that particular control at the end of the day. And the best parameter measured against is cost per ton of control when it comes down to it. Well, how much is that cost per ton? What's a reasonable number? Case-by-case evaluation. Last thing you'll see in print probably is what that number is, because the agency wants flexibility of making up its mind on any given project. But again, previous projects, if you're getting to a point where you're really trying to decide between 2 technologies and really trying to eliminate one that won't get off your list, you can go back to other permit applications and see what cost effectiveness they wound up with that was accepted and what ones were rejected, and use that as well. That's not going to show up in the permit as far as the technology that was applied, but it will show up in the applications. For that, it's an extra step. You have to FOIA that. That's generally not public information that's handed out. You have to go get it. But that analysis is like when we do our analysis and eliminate things, that's all shows the dollar amounts that those above the line and below the line. And you can use that from other applications as well. They keep it case by case because they want to keep it different for different pollutants. CO maybe doesn't matter as much as VOC in a non-attainment area, for example. Cost-effective base, slimmer controlled sources. And like I said, the US EPA doesn't have a bright line number, and neither do most states. Show me the money. San Diego County is one of the exceptions. They actually have a website that publishes, they try to keep it up to date on what the cost-effective dollars per pound of pollutant is. In this case, VOC, for example, is $6.60 for sources less than 15 tons per year, and $9 a pound for greater than 15 tons per year. So if you translate that to tons, that's 9 times 2,000 is $18,000 a ton. What do we tell people? You know, if you're in the $10,000 to $15,000 range, you're probably in the right range for arguing it's cost effective. If you're above 15,000, 20,000, you're probably getting in the range where you can justify it as not being cost effective. So clearly at 100,000, that's way too much, and $500 a ton is clearly cost effective. So San Diego is one of the few that actually draws these lines. So $18,000 a ton. This for less than 15 tons, it's only $12,000 a ton. So again, that's in that same range. You can think of between 10 and 20 as being kind of the gray area. Anything above that or below that is generally accepted. Anybody have any different experience on that, where they've got locked in something more expensive than that or less? But this is very unusual to have a state actually come up with one. What are the expectations? Again, what's in similar control processes? What's been issued as BACT for someone else similar? If it's presumed that the control technology is cost effective, if a similar type and size of source is using the technology. So no matter what your number comes out, somebody else is using it already and has been using it. They assume that's cost effective for them. It's got to be cost effective for you. Even if your numbers show $30,000 a ton, somebody else is doing it. Obviously, they can afford $30,000 a ton. You should be able to afford $30,000 a ton. Whether that's true or not is up to your financial people. And then finally, when evaluating control effectiveness for a given technology, applicants need to consider various levels of control depending upon the control too. So again, you can have dust collectors work at various levels. You know, scrubbers work at different levels. There's different things you can do to change that effectiveness. Even a combustion source, if you add more fuel to it, you generally get better combustion of what you're trying to burn than if you don't. But that's at a cost. And so those ranking of your control technologies sometimes rank not just the type of control, but the level of control, and each of those levels of controls have different costs associated with maintaining that level of control. And those should be part of your analysis too. Don't say it doesn't work because at 99.9% control it costs $1 million a ton. They say, well, if you ran at 99% control, it'd only be $10,000 a ton. And so you have to consider the same control technology at maybe different levels of controls to make it cheap enough to institute and not just eliminate completely. And I've seen those pushed as low as like 80% control on something if you ran it cheap enough to make it cost effective. You'd only get 80% control instead of the 99% control you'd run if you ran it at what was intended to run.
Whenever we installed a heater, a platformer heater after our big expansion 4 or 5 years ago, we put SCRs on all the heaters for the big expansion, except for the platformer. And the reason we didn't for the platformer was because it was too big.
Right.
It was the largest heater in North America. It was over 1 billion BTUs per hour. And no one said they could design an SCR for it.
Right.
And it was just too big.
So that was a good example. SCR was BACT for everything except that one,
That one monster heater.
because it fell out at a different level. Yeah.
And so they were asking us, well, we'd split it up into 2 heaters, and then it was going to increase the cost dramatically by having 2 half billion BTU heaters.
Right. That's looking at different emission unit sizes for the same source.
We did. We put SCR on every other. We have SCRs on heaters that are under 100 million, and
Oh, that's a good example.
Yeah, that flew.
Yeah, yeah. And like I said, all the reasons we just stated, it actually fits into the model for the right reasons that way too, so. But that's also interesting, you mentioned they did ask you to change the design of the project at one point to see if that would meet the requirements or not, even though it wasn't the original
It would
design.
work, but it would have been a lot more expensive to
Right.
do as opposed to.
Now think of yourself, if you were in the layer realm, that wouldn't have been a choice of cost effectiveness wouldn't have came into it. They just would have said, if it's technically infeasible to do it, then make it small enough to make it technically, and then at whatever the cost.
They had made us do that?
Yeah,
Put in 2 heaters?
yeah. BACT follow-up. BACT must be current at the time the permit is issued, okay? Like I said, BACT, one of the first things you want to do when you trip into BACT to make sure your design is correct, your BACT has to be current at the time it's issued, not at the time you submitted it. If it takes a year to get it, it's really on you to keep that BACT that should still be current a year from the time you submit the application with all this analysis done. And agencies have gone, especially when they get, a year or 2 year old, to go back and somebody's put in something newer, those NOx rates have been ratcheted down, go back and change it. And then of course you change that number, it changes all your math, changes all your emission rates and everything, your table. So keep that in mind that once you submit the BACT, it's not final as far as the agency is concerned the date you submit it, it's only final on the date you get your permit. And for multi-phase projects especially comes into play, that something's going to be spaced out maybe over 10 years, a third of it every 3 years, and you have to do a PSD because it's an aggregated project, one planning cycle, you have to do a PSD for this whole project. You determine what BACT is for the whole thing up front, you get your permit, and then 6 years later, BACT's changed a lot, and your third stage of the project, you might have to reevaluate the BACT for that and make a new demonstration for it. By then, you're 2/3 of the way into the project. They really have around the neck for what the requirements is, but it's a requirement that, again, at the time for multi-phase projects, you have to keep up to date with that until the construction actually starts. Okay. Revising BACT determination post-permit. There is one memo on that point. It goes all the way back to 87. One, the source was constructed in conformity with the permit. The permit levels are inappropriate for the resulting of errors, faulty data, or incorrect assumptions. It turned out that the vendors promised this would work, but they forgot to tell you it only works up to a certain BTU value, and they can't deliver on it. So now you got your permit, you're ready to construct, and you can't do it. You can resubmit post-permit, the BACT, a new BACT determination to justify what you're actually going to put in. And the last one is the source investigate all available options, reduce emissions, and demonstrate that compliance cannot be achieved. This happened a lot in the peaker days where guys were promising lower and lower NOx numbers to get your permit through faster and faster. Well, they started promising stuff they couldn't deliver on, and no matter what you did, you couldn't operate the turbine or the boiler at that level. It just wouldn't work. So there, it's no fault of your own, except you trusted the vendor to deliver. If they couldn't deliver, you document that it's impossible. You tried everything. You tried tune-ups. You tried everything. You submit that, and you get, at that point, it's possible to get a relaxation of that BACT limit to some higher level as a result of being demonstrated that the other one's not feasible. So if you knew it wasn't going to be feasible, it would have fallen out in your step 2 of your analysis right anyway. So it fits into the model, but it's awkward, and believe me, it's like Randy said, Lucy's got some explaining to do if you get into that scenario.
We had one of those issues. Vendor promised they could do this, they couldn't do this. They tweaked it, and basically they came back and said, "Okay, we tried, sorry," and went.
Not enough explaining.
we went through. I went through all the contracts, and they was going to do this emission rate at this fuel gas, these certain conditions. So we went and we mimicked their conditions as best we could, and that was difficult enough to get the fuel gas. It still didn't meet, and they basically, vendor told us to go to DEQ and tell them to change it. And I said, well, you know, people can meet this, so you should be able to meet this. And they said to Vicky, I'm sorry, and you're on your own. And then I had to get our attorneys involved, and they called their attorneys, and that's apparently what it takes. And then they got on a plane and flew down there and really worked really hard at getting it to work, and it worked. That's what it took. They were basically just gonna wash their hands of it. They didn't wanna invest the money. So, it's amazing that, these are also on burners.
Yeah, I think at that point, if it didn't work even after that second time, under the penalty of law, that they, contracts, and if it didn't work at that point, you probably get the agency to change your BACT at that point,
They were
but,
gonna fix it because we were gonna make them give us our money back and go buy some.
yeah, that would
It was
work, right?
Amazing, you know, we're a big facility, we spend a lot of money annually, we thought that they would bend over backwards to try to help us
Yeah.
out. So the fact that they just said sorry, that was kind of a revelation, I didn't realize they did. I'm worried about future.
Okay. Well, it is tomorrow already, for the greenhouse gases, so, let's go to the next, I think you're up for the greenhouse gas part. Talk a little bit about the greenhouse gas stuff here. It's in the other program here. You know where these things are. You gotta go back to day 3, day 2.
All right, bear with us for just a few more minutes, and we're gonna take a 10 o'clock break. So y'all
Yep.
can all go down and figure about that.
Yep, we'll have break 10:30 again, and lunch noon to 1, and then our 3 to 3:30 break. And since we messed up our timing yesterday a little bit on our afternoon break, we didn't get to see the fish races, so we'll make sure we break by 3 o'clock so we can get down to watch the fish races. Remember, it's a demonstration, not a competition. Please, no wagering.
All right, we're gonna shift gears a little bit, but not too much, and talk about greenhouse gas permitting. But before we proceed,
I have one question, Dr. Frankenstein. That's Frankenstein.
okay. Any questions before we go into greenhouse gas? Any other BACD questions? I'm going to go through a few of these slides. You guys know this stuff pretty well. The tailoring rule kind of, it resets some of the problems with the major source definition, so they could bring greenhouse gases, magic numbers now, 100,000 tons CO2 equivalent, 75,000 tons for a modification. It also factors in these global warming potential factors where we convert various greenhouse gases to CO2 equivalents. So we got our movie quote on conversions that don't seem right is Marilyn Monroe, of course, and Some Like It Hot. Real diamonds, wow, they must be worth their weight in gold. That's kind of how I feel sometimes. I'm going to blow through this so we can hopefully wrap up our greenhouse gas, leave a little bit of time for discussion before 10 o'clock. But you guys know these numbers. Like I said, the magic numbers being mainly 100,000 for non-listed source categories, 250 tons per year, 75,000 for a CO2 modification. That's the number most of us are concerned about. All right. So a lot of us went through, we've actually got a greenhouse gas expert in the room. No one's probably done as much of this as anybody. But I took credit for all that work, so I'm up here talking about it. You know, we got a number of greenhouse gas permits before this Supreme Court ruling, and at least one of mine was fell in this anyway source. It was greenhouse gases were the only thing that triggered federal review because this source had a PAL, so nothing else triggered. So we went through this incredible drama to get this greenhouse gas permit. We negotiated with EPA, and they beat us bloody, and we recovered and finally got our permit. And then it went to the appeals board, and then they did their little thing, and then finally issued the permit. And right after that, of course, the Supreme Court ruled and said, look, you guys can't regulate greenhouse gas pollutants under the PSD rules unless something else triggers, unless another pollutant triggers. So that's where we are now. So
You're a survivor.
yeah, I am a survivor. I didn't get a badge or anything, but I survived it. But I think we learned a lot through the process. But this is where we are right now. There's a lot of drama with greenhouse gas, especially here in Texas. Just to kind of give you guys some rules of thumb to look at when you're looking at modifications and you're putting in a new fired source. You know, usually natural gas, you can hit about 75,000 tons CO2 equivalent, somewhere around 150 million BTUs per hour. For refinery fuel gas, that's going to be more like about 131 million BTUs per hour. And these are just kind of based on the Part 98 factors that are in the Subpart W rules. So that's just kind of a nice rule of thumb when you're talking to your project people. Well, I wonder if we're going to trigger greenhouse gas. Well, how big is your fired source? And that'll let you know. Greenhouse gas permitting is a little bit different from some of the other pollutants now. It's PSD, it's obviously non-attainment. I guess the whole planet would be non-attainment. So there's not much of an alternate site analysis required. But besides that, you can treat CO2 equivalents pretty much like any other pollutant. You can do project netting. You can have a BACT. There's no modeling requirement, of course. Title V requirements, but the fees usually aren't based on the tons. And you could have some other federal, state, and regional application requirements. I got a movie that kind of started a lot of the stuff. Al Gore and Inconvenient Truth. I like this quote. It's a Mark Twain quote. It says, "What gets us into trouble is not what we don't know, it's what we know for sure that just ain't so." So, you know, that could flip back and forth on either side of this whole greenhouse gas controversy. Okay. What's the big deal with greenhouse gas? It's doing the BACT analysis. And Taras, you mentioned that earlier, all the navigating this 5-step top-down approach for greenhouse gas is crazy. And I'm hoping it's going to get a lot better in Texas, since Texas has now got delegation of the program. But when EPA Region 6 had it, we were implementing under a federal implementation plan, or a FIP. And wow, was it ever fun dealing with an agency that hadn't done permits, you know, since I was there in 1980, working as a young permit engineer. It was before Texas got delegation, and we were doing all the PSD permits out of the region. I worked there for a couple of years to pay back my student loan. So they had no experience really working these issues, and they got real carried away with all the cross-cutting issues, the environmental assessments and the cultural resources, and you know, all of a sudden you're dealing with a fish and wildlife. You know, it's just kind of scary to think about. I think all that's going to, well, it's going to improve, because now that Texas has taken over the program, these permits aren't issued by a federal agency, and there's not the requirement to check the box and all these other federal regulations. So these cross-cutting issues will now, by and large, disappear when Texas takes over the program. We'll still have BACT and everything else, but like Tarat said, you know, the benchmarking on energy efficiency and good combustion practice seem to be at the meat of the matter. You know, I think those are legitimate concerns, and I think we'll still get those kind of questions, and you'll need to address those, and that's really what the BACT is going to center around. You know, it's not like any of you guys are in the business of wasting energy or being inefficient anyway. So, you know, these things are already incorporated in your design. It's just that now, for the first time, the agencies are more involved in that technical engineering process. than they've ever been before. And they're asking all those questions.
Wasting energy. Some power companies in here, isn't it? I mean, basically, power companies, I mean, the more inefficient they are, the more profit they make, especially those that are regulated by Public Service Commission, correct? They make a certain profit on their operating costs, so it's in their best interest to be as efficient as possible. Isn't that really the whole key behind this greenhouse gas? Is that,
I don't know. I mean, we're talking about the politics, and you know, but I understand your concern. At some point, you know, I can make the same comment about my business. You know, we sell hours, so the stupider we are, the more hours it's going to take us, and so the more money we can make, right? The more mistake. But at some point, that comes back, and they're going, oh man, those guys at Sage are idiots. Don't ever hire them. And then
it's easy to replace Sage, but it's hard to replace power company
Yeah.
down the road.
No, I agree with you. I mean, to me, it's a political concern, yeah. Yeah, because they can raise rates and do it. They're different from you guys, though. You guys couldn't exist like that.
No, we could not, but I know that, you know, it is in their best interest and they do as much as they can to operate. They could replace the old turbines with new turbines when, you know, whenever it's time to replace the new turbines with more efficient turbines, but they.
Do you get the feeling?
Not.
You get the feeling maybe these greenhouse gas rules will drive them that way?
Not in this particular format, not in the NSR regulations, but if they would, maybe if they would have done it a different way, they could have.
Yeah. Yeah.
And this is a backdoor way of trying to get them to go that way, right?
Yeah. All the applications I've worked at, that's what they drilled down on. You know, they wanted us to benchmark with all kinds of other efficiency ratings, star efficiency ratings, and you know, when you could probably speak to this better than me, but you know, there's a lot of benchmarking questions in there, and even not only just the other units in our facility or our source, but industry and other industries. So, I mean, I would think that if they treated the power, I've never done a power plant, greenhouse gas, but I would think if they treated them that way, you know, they should be getting those same kind of questions. Whether they do or not, I don't know.
Well, I know that there's lots of power plants that went in and they would have changed out turbines and it would have triggered NSPS, but they didn't hit the 50% threshold because
Yeah.
they didn't increase emissions, so they were able to skirt updating their turbines through NSPS. So another way to get them was in the back door by sticking in
Yeah.
NSR.
Well, I think what you guys can expect are significant questions on flare gas recovery. And they're going to hit that on heat conservation and just kind of some general pollution prevention measures. I mean, that's what I saw more than anything else. And you know, I think those are probably fair enough questions, and they're questions that certainly you guys are going to build into your design anyway, just for cost reasons and fuel reasons.
We are seeing more interest in the capture and sequestration issue too. Before you pretty much had a pass and say, we realize that's not cost effective anymore. But now we're seeing more requests to put that in there on a site specific basis and check it out. Either for, again, through this 5 steps, either step 2 or step 4, saying either it's technically not feasible for us to capture the CO2 in our process because it's a loose stream or whatever, or 2, it's not cost effective for us to build our own pipeline down to Texas from Iowa.
Yep.
Use it in oil gas recovery or something. So instead of just giving you a free pass saying that technology hasn't gotten here yet, they're going to more and more require you to come up with at least some benchmark costs for what would cost for you to do carbon capture and sequestration.
Yeah, we got some slides on that in a moment. I wanted to point out that this website is actually pretty good. It's unlike the backrack clearinghouse stuff, and I'll show you why in just a minute. It's pretty current, so I'm probably going to miss that one just a little bit. But this is what Bruce was just talking about. The challenges that I see are with CCS, at least that's where they've been historically, and they're EPA didn't let us drop anything out at step 2. They made us run all the way through it, just like Bruce said, with really specific equipment volumes and tell us, what is it going to cost to capture, what is it going to cost to compress gases that aren't high concentration streams, how are we going to transport it through the pipeline, and then, how are we going to store it? So, there was no common sense in any of this. Even though the guidance manuals talk about some common sense approach, that these should be high concentration, more pure streams that are selected for this. EPA was making us go through everything. I don't know how Texas is going to do it. I don't know if they're going to do a top-down sort of approach, similar to what we've been seeing, or whether they're going to go to a more tiered 3 sort of approach, or some hybrid. I suspect some hybrid type of approach is what they're going to see for these BACT analysis. But that's the first one. Carbon capture is probably going to be a booger still to get by. We're already starting to see some NSPS regulations for refinery and electric generating units that are going to set a back floor. Maybe that's what they're going to use. Like Taras said, there's a push by EPA to evaluate on a percent of the capital cost rather than $1 per ton. That really drives me up a wall. We got questions, the same questions you did. What is the percentage of the project cost? Well, we didn't want to put that in the public record. We just didn't, and then, so we avoided the questions over and over again, and they just kept coming back to us. Well, is it more than or less than 25%? We didn't get 66%. More or less than 25% of the capital cost. We're going, hey, the capital cost of this project is $3.75 billion. 25% of that is a large chunk of change. And you're going to evaluate this on a percentage of the capital cost. So what you're saying is, I'm going to penalize the big guys with big projects. If I'm small enough, doesn't matter what my $1 per ton cost is. We just found this pretty incredible that EPA was saying that kind of stuff to us. So, but we persevered and basically told them, our cost per. We just kept going back to that cost per $1 per ton, and eventually they left us alone. Did you have any?
So the big push for that was Sierra Club.
Yeah.
Sierra Club, on all the permits that they commented on, said you can't do it the way the EPA was doing it. You have to evaluate it on $1 per ton. And so the EPA kind of threw up their hands and said, all right, we want both. And they always, up until the Emit, always said, give us the cost per capital. And they would accept what y'all were saying in that, it's greater than 25%. We'll show you off to the side. We'll say it costs at least this amount, but not give you the real number, the amount that triggered the 25%. But companies, in order to avoid comment from Sierra Club, started putting in that $1 per ton amount just to get away from slowing down the permit. I don't know. I assume TCEQ will do the $1 per ton.
Yeah, I'm assuming they will too. And I don't have any fundamental issues with the $1 per ton approach. That's consistent with BACT, and I think that's justifiable. Another challenge we saw was the EPA push for numerical limits, or in the absence for justification for best management practices. We saw a lot of exit step temperature requirements going in. Your stack can't be above 240 degrees F on the release. They want you to do some heat recovery for energy efficiency purposes, and that's going to be monitored now, and all that. And then the cross-cutting evaluations, like I said, the biological assessment, and cultural, historical, all the various agencies involved. It just became a timing nightmare. Got a movie that, one of the first movies to recognize the seriousness of cross-cutting issues was, of course, The Great Vincent Price and the Pit and the Pendulum. he had some real cross-cutting issues there. Greenhouse gas BACT, you know, the Office of Air and Radiation, which I worked for in 1980, came out with some guidance that EPA absolutely does not follow their own guidance. So, but I thought I'd mention it. This is the table of contents, and it goes through and you can see in Chapter 3, it goes through the top-down approach and other BACT requirements. I'm probably going to go through some of this pretty quickly because we're about to our break time. So I mentioned this earlier, so I'm going to skip that slide. This clip reminds me more than any other clip that I've seen in the movies about EPA's attitude toward carbon capture sequestration. They really want somebody to have carbon capture sequestration. They really do. I mean, it's just like a bee in their bonnet. And I recognize this, but it's probably not going to happen in any of the industries represented in this room. It just doesn't make sense. But this is how I feel about EPA's.
What do you think the chances are of a guy like you and a girl like me ending up together?
Not good.
You mean not good like 1 out of 100?
I'd say more like 1 out of 1,000,000.
So you're telling me there's a chance? Yeah!
That's how I feel, EPA. Yeah! There's a chance we're going to get it on this application. Okay. I'm finished with the silly for a few more slides, I guess. A lot of drama in Texas. I'll wrap this up pretty good. I mean, when I got this letter when Texas refused to implement greenhouse gas, I'll never forget the day I was sitting at my desk. It's like the day that Challenger or Kennedy was assassinated or something. This is another one of those days that I always remember where I was. I was sitting at my desk and this letter came back, and I thought, this is the greatest farce I've ever seen. This is the funniest satire I've ever seen, and it was a letter from Shaw and Abbott, who was the Attorney General of Texas, to Jackson and Armendariz, who is Regional 6 Administrator. In the first line, I can't help but do this kind of stuff. In the very first sentence of the letter said, in order to deter challenges to your plan for centralized control of industrial development, through the issues of permits for greenhouse gas to encourage acquiescence with your unsupported findings, you threaten to usurp state enforcement authority and to federalize the permitting program of any state that fails to pledge their fealty to the Environmental Protection Agency. And you're not even out of the first paragraph yet. It just goes on and on. It's great reading. It's in your jump drive, so good, funny reading. It backfired on Texas. You know, what happened is EPA Region 6 got it, and the delays were greater than anyone anticipated, and it completely backfired because it worked toward uncertainty in the permitting system in Texas. You had to now get your NSR permit with TCEQ and your greenhouse gas permit with EPA Region 6, and it resulted in a lot of industries going to Louisiana or you know, no telling what. But there was just so much drama and uncertainty that I think it hurt. And of course, my movie's The Texas Chainsaw Massacre here. But it got corrected. You know, there was finally an industry-supported bill that went through, moved the program back to TCEQ. Brian Shaw had another quote. While the state continues to disagree with the EPA program to regulate greenhouse gases, TCEQ has a system in place to ensure timely permitting. It provides stability, predictability to our state regulatory framework. So this did a number of things besides just kind of move the review from Region 6 to Texas. It also eliminated this Environmental Appeals Board avenue for SIP-approved programs. So now you can your appeal, you can still have an appeal in state court, but the permit is not stayed pending a final decision. On this crazy permit that I worked for, there was an anyway source, which we absolutely didn't have to do now. We went through all this trouble to get it. And then we got an Environmental Appeals Board request. And so it was like you had a contested permit hearing, and then you had this drag out for EPA issuing the greenhouse permit, and then you finally get your permit, and now you got an Environmental Appeals Board, and you still can't begin construction because the permit was stayed. Well, that's corrected with TCEQ taking over or it's bettered with TCEQ taking over the program. It can still go to a state court, but your permit's good, and you can begin construction. So that's one of the things. There's still some uncertainty whether they're going to have be top down or whether CCS is going to drop out at technically infeasible or economic evaluation. This is the site, the Greenhouse Gas Region 6 website. You can actually click on these, they're hyperlinks, and you can get right to the exact document that's in here. So it's kind of a neat link if you want to know, what a public notice is or what a draft cultural resources report looks like. Just go in there and click on that link, and you've got them right there. So that's it. Deficiencies are mainly around benchmarking and BACT and monitoring and record keeping. I think we probably covered some of this. There's thermal efficiency requirements, exit stack gas requirements. All these things are kind of written into the greenhouse gas permit. There's a DRE requirement, all these kind of things. I've just kind of pulled up some things we've seen in various permits that were issued. Heating value contents.
How much fuel you use and how efficient the engine is to burn it. There's no add-on controls you can do to eliminate CO2 from going into the atmosphere.
Yeah. There's some NSPS proposed rule status for new power plants and for existing and modified power plants. And of course, the energy folks are squawking about it again, just like you were mentioning. This is a graph put up. Notice this is the American Coalition for Clean Coal Electricity. So the factors might be biased just a little bit, but they're saying, okay, this is what you can expect for energy price increases after they do this greenhouse gas NSPS. Our prices are going up. And this is what we estimate they're going to go up for due to the transport and MAERT proposals. So kind of blowing through some of all this, but I wanted to get you to your break, which I think we've done now. So we went through how to avoid PSD. Then we said, okay, your PSD. What are the two main things? They're BACT, which we went through, and modeling or an impacts evaluation. So we're going to spend a little bit of time, hopefully before lunch, we'll see how far we get, talking about modeling. And when I sort of put together a modeling presentation, I wanted it to be geared more toward a permit manager and give the permit manager the necessary concepts and tools and explaining on a little bit higher level than I would an actual dispersion modeler who's clicking the keys and wondering if he should use a low or medium surface roughness factor and all that kind of stuff. So I thought the best way to do that might just to go through a case study and evaluate it that way, with the objective that with the objective being that we could equip you as a plan or permit manager with the necessary concepts and tools and policy information so you can manage your modeling project. And so some of the unnecessary controls and operational constraints that could be incorporated in your modeling could be avoided. Okay, so that's where we're headed with this. And with that mission statement, I'll give you one other great mission statement in the movies.
We're on a mission from God.
Okay, that's it. Well, these are not our course goals, so if you intended to discuss technical modeling issues or to enable you to fluently gauge your modeler in their native tongue, which by the way is algorithmicese, they speak in algorithms. If you're hoping to attain the latest information regarding the response surface model metamorphic modeling technique that aggregates numerous pre-specified air quality modeling simulations into a multidimensional air quality response surface, then you're out of luck, because we're not going to talk about that at all. These are, of course, Revenge of the Nerds, and it's a little known, but these guys are now SAGE modelers. They're part of the SAGE modeling group. They used to be in the Revenge of the Nerd movie. But we are going to cover this. We're going to cover some of the historical background, where modeling fits in the permitting process, and how the model works, like I said, on an executive level. Going to touch some of the new NACs and why it's tougher than ever to model out with some of the new NACs, and go through some recent policy papers that hopefully will give you a few things you can do in your modeling analysis to pass. And like I said, we're going to do this in a case study. And the case study is mainly going to be, how do we troubleshoot our model? How do we figure out what our culprits are, why our model's not passing, and how do we adjust our model to get us a passing analysis? And usually that's going to mean getting under the significant impact levels, or what I call the SILs. Because if you don't get under that, you're going to be modeling the rest of your facility site-wide, maybe everybody else's facility. They're going to be the odor, NOx emission control levels. It's going to be harder to pass a NACS or an increment analysis when you do, okay? So here's what we got. We got our case study basis. It's Rising Sun Chemical Corporation. It's their ABC project. And we're going to go through all these different pollutants and talk about how we get a path forward for NACS compliance on all of them. Rising Sun Chemical motto, of course, is you'll just love our ethylene. They're an ethylene plant. I made all this stuff up. Project background is Rising Sun Chemical wants to expand their worldwide ethylene production to Port Arthur, Texas, lovely East Texas in the Golden Triangle. And although ethylene producers worldwide, this would be their first U.S. plant, codename ABC. And Rising Sun purchased an existing operation, but will expand its production immediately. The economics driven by low feedstock, the ethane prices on the U.S. Gulf Coast are driving the project. Our movie code, of course, is from The Graduate, and it's a one-liner, a one-word, plastics. Remember plastics? I don't know if you remember that. But here's the deal. You're assigned the environmental manager for the site and expansion, the largest in Rising Sun's history. So you're the environmental manager. They purchased a modest existing facility, but the new ABC ethylene production project includes all these different emission sources associated with routine furnaces. I mean, routine operation. We got decoking furnaces, decoking vents, cracking furnaces, flares, cooling tower, equalization tanks, yada, 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 fugitive areas, ammonia tanks. We got all the things that go into a major modification or major expansion. And we also have MSS because we're sitting here in Texas, right? So we've got furnace maintenance, decoking vent maintenance. We have a ground flare for intermittent vents, a ground flare for our startup vents, acetylene converter vent, generators, fire pumps. We got the whole gamut of things here, right? And then we have all our other maintenance stuff, our sandblasting, our painting, our vac trucks, our tank cleanings, all that kind of stuff that we've got to consider here in Texas as part of our permit application. So here we are, ABC. You can see Houston there and pretty close to the Louisiana border, right in beautiful Port Arthur. kind of bringing it down to the facility location. And we found this nice plot of land, and the existing facility is over here in the corner. But this is going to be our facility. And so our site selection, our purchase acquisition has been completed under your direction as the permit manager. The preliminary design information supplied to your environmental consultant. The emission calculations have been done. The PSD triggered for almost all pollutants. You got your application in. It was deemed administratively complete. Submitted to TCQ 7 weeks ago. You're on schedule for a start of construction in 14 months. The whole world looks bright and shiny to you. You did your first 30-day public notice. It's nearing completion. Then TCQ sends you an NOD letter requesting modeling, and it's a notice of deficiency letter. And Rising Sun's CEO and CFO do not tolerate deficiencies. And as project manager, you're most concerned with item 12 of the NOD that requests dispersion modeling. Previously considered the Rising Sun or Rising Sun, you begin to consider how a permit modeling schedule is going to affect your career, right? So what did this NOD letter say? We've all gotten them, right? Tammy, you ever gotten them? And it all says pretty much the same thing, right? This was item 12. I'm not going to go through the first 11 items, but here's item 12. Please supply a demonstration that the predicted concentration of air contaminants outside the facility will not cause or contribute to a violation of any applicable NAAQS. You can make this demonstration by showing the predicted effects of the proposed increases will be authorized in the proposed permit action will not exceed a significant level. So they're saying, model your project. You can show that if your project doesn't exceed a significant level, you're okay. You may modify your proposal and emission rates to facilitate making this demonstration. Please feel free to reduce your emission rates to pass modeling, right? Nice. TCQ may not approve a proposed permit action if this demonstration is not made. If you cannot supply this demonstration by the time limit stated in the letter, your application will be voided. Please provide modeling results that satisfy the requirements of 30 KC 116, yada, yada, yada. Provide information demonstrating that the emissions of the facility will comply with the intent of the Texas Clean Air Act. So we got these NAAQS here. Now they're asking for something different, including protection, public health and welfare by performing a health effects review as well as your PSD review, right? According to the TCQ guidance, if you determine that refined modeling yada, 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 you need to use AirMod, provide a timeline, okay? So you're getting this, and you're not sure what it all means, but you understand enough of these words. Supply a demonstration or your application will be voided. AirMod modeling is going to be needed. You need to submit a protocol, you need to submit a report, and you make one of the best career decisions in your life at this point. You decide to call your consultant before you relay this information back to Japan, right? So you meet with your consultant early the next morning and you stress that you're going to have to explain this TCEQ notice of deficiency letter and path forward to Rising Sun CEO tomorrow in Japanese. And the question the CEO is likely to ask are, what is modeling? What's dispersion modeling? What's AirMod? Application voidance will not be tolerated. Do we have the information to respond? Was this expected? Is it going to impact schedule? Is it going to impact cost? All of us have been there, right? I noticed the movie The Day After was on the table last night. So anyway. Consultant says not to worry. Consultants are like that. The letter is a form letter. TCQ is not going to void the application as long as we respond in a reasonable amount of time. We anticipated this. It happens all the time. We have the information we need to do the initial modeling. Should not affect schedule. No problem, says the consultant. They're happy to help you with the PowerPoint for your CEO call and address these things. What is dispersion modeling? What inputs are needed? What's an NAAQS? Says, by the way, we didn't include this in our cost estimate for the model, but let's just worry about that later, right? Modeling costs are soaring. Marcus probably has personal.
What the consultants don't realize is that we usually factor in some of this in our PO anyways.
Smart man. Smart man. That's becoming more and more.
I would rather come in under the PO than have to go back and ask for more.
I know, it's insane. So you got your CEO briefing on dispersion modeling, and so what is dispersion modeling? And the consultant lets you know that it's the mathematical simulation of how pollutants disperse in the atmosphere. About as good a definition as I can think of. And in this context, in the context of modeling for PSD permit, air dispersion modeling works by putting in numerous variables into a computer model, and the computer model is going to predict the maximum off-property impacts of the pollutants. And it's really the only viable way to predict impacts from a proposed unit, right? You can't go out there and measure them or monitor the emissions at the fence line because the thing's not built yet. So you have to have some way to predict what the impacts are going to be, and that's probably 95% of the use of dispersion models these days is in prediction tools. So that's what we got, and you're going to tell your CEO that these models have been used for probably 40 years now, and they've been standardized for regulatory applications, and the one that we're going to use is the AirMod model, which is the preferred model now for PSD applications, and it means American Meteorological Society EPA regulatory model, AirMod, okay? That's it. The purpose of the modeling is going to be to estimate the air pollutants off-site. It's going to model these ground level concentrations, unless we tell it to model something on a hillside or a flagpole or something like that. And then we're going to, it's going to be at locations that the public has access to, and then we're going to compare those predictions to our National Ambient Air Quality Standards, and in this case to these TCQ effect screening levels for particular compounds, which the toxicologists at TCQ will evaluate to see if we're okay or not okay. All right. What do we put in the model? We put emission rates, we put emission release information like stack heights and velocity and temperature. We put the receptor locations, which is just a location where you want the model to predict the concentration. We'll talk about that in a minute. Metadata, and then how you want the model to spit out the output, what averaging times, and whether it's a 1 hour average, 3 hour average, 24-hour average, or annual average, whatever. So as far as our emission rate information goes, it's just the information out of our application. We've already done those calculations. We're going to pull that out, and that's going to be our starting point. And includes, like I said, all these routine and these MSS operations. And it's going to include short-term averaging periods and long-term averaging periods that line up with however the National Ambient Air Quality Standard averaging period is, okay? We got point sources, we got area sources, we got volume sources, and this is all intuitive stuff. Point source is like a stack, it's a single point of release. An area source is one that's best represented in 2 dimensions, a flat source like a lagoon or a pond or a wastewater pond, and could be even in a top of a cooling tower, or any number of things could be done. A volume source is best representative in 3 dimensions. It could be a process area where you have a lot of fugitive components over a 3-dimensional field, and you might choose to model those sources like an area source, okay? And that's just kind of stuff modelers do, but why are the emission rates important? The emission release input's important. All we're doing with all these emission releases, we're trying to determine how high the plume goes. What is our plume rise before it starts to disperse? and a Gaussian distribution back down to ground level where the public has access. So the more momentum, which is the velocity times the diameter, the more flow that comes out of there, the more momentum we get, the higher it's going to go. The hotter it is, the higher it's going to go, hot air rises. And, you know, it's really pretty simple in terms of those concepts, but all those go toward determining what the final plume rise is before it begins to disperse and go back down to ground level. All right. So these point sources, I'm going to kind of blow through some of this stuff. The model's fairly sophisticated. It takes into effect downwash influences, and that's just kind of the cavity turbulence zone where the wind's blowing through a building. You know, there's some downwash effects or cavity effects. So you put in your building dimensions to account for that kind of stuff, and there's numerous algorithms that calculate, you know, at times that actually helps your dispersion. It distributes over the length of the building. At times it hurts it. It brings the plume down to ground level faster than it would normally be without any downwash. So there's flares, which are special point sources. You know, flares get that final plume rise mainly from the heat of the combustion of the gases going to the flares that are burned, just like a big fireball at the end of a pipe. And so it depends on what compounds are going to the flare, what your heater release is, and they use that heater release to kind of trick the model into predicting a final plume rise that's equivalent through this calculation that's called an effective diameter calculation. I'm not going to go into all that right now, but it's just a way that it's a mathematical simulation to get these two I'm not going to get too technical. I said I wasn't going to do the metaphysical aspects of higher dispersion philosophy, but it's basically setting these two plume rise equations equal to each other and solving for 3 of the 4 variables. So you've got this little calculation to calculate effective diameter that would give you the same plume rise because of the heat of combustion. So that's probably enough said about that. You got pseudo point sources, which are just like, I don't know what to do with this thing. It's just a little, it doesn't have any momentum. It doesn't have any temperature. It's just a little point here. So I'm going to call it a pseudo point source and give it no velocity, no temperature, and of course very bad dispersion. But it's just a way to deal with small things. So you do all this, and you set up a receptor grid around your plant. And all your receptor grids is all these discrete little points all the way around here where you're asking the model to calculate a concentration. And you can see they're real dense up close to the property line where you expect maybe your maximum concentrations to occur. And as you move out with increasing distance from your emission sources, the receptor grid is more widely spaced, right? So it usually extends out about 10 kilometers at least. So this is kind of backing off and showing you how a typical receptor grid for one of these works. And what you're trying to do is just capture the maximum concentration off property, right? And you know, if it's a flare, it could be coming out here, and if it's a fugitive source, it's going to be one of these right around the property line. So the MET data is pretty intuitive. It just kind of defines the amount of turbulence and mixing in the atmosphere for different weather conditions, and it's actual MET data, and usually it's pre-processed and supplied by the state agencies. So this is as technical as I'm going to get. This is how you're going to explain to the CEO how dispersion modeling works. AirMod's a steady state Gaussian model with a plume extending downward in a direction source. Let's see if I can get this thing to work. Is there a pointer right here? Ah, okay. So you have your stack right here, and the wind's blowing this way. So your plume rise is going to be right here, and then it's going to start dispersing in a Gaussian format, kind of bell-shaped curve, both in this direction right here and in this direction. So two-dimensional Gaussian dispersion, and then what you're doing is you're getting a concentration at your plume center line when that plume hits the ground level, right? So it's going to do dispersion in the vertical and horizontal axis following a Gaussian distribution. So here's the Gaussian part of it. And the source conditions like the emission rate and the temperature and the velocity and the MET conditions, they're all constant for a 1 hour time step. So for every hour of the year, they're going to be 87, 60 hours a year, right? And for every hour of the year, you're going to have a velocity, you're going to have a stack height, you're going to have a emission rate, and you're going to have the MET conditions for that hour. And the model's going to predict what that concentration is at every one of those points I just showed you on the previous slide, every one of those receptor locations for every emission point for every hour of the year. And it's just going to, I mean, you can see how it's kind of mathematically intensive, but it's just going to historize that hour 873 or something, had this concentration at this location, this location, this location, this location, this location. And then it's going to go on to the next hour. And when it goes on to the next hour, it completely forgets about the hour before it. The wind direction might be completely different the next hour. It might be in the same direction. So you don't get the effect with these models of a plume that goes so far in 1 hour and then the wind shifts, so it goes up here and the wind shifts again and it goes back over here. It's just 1 hour time steps. And it saves all that information and then does all the averaging periods for every receptor location, like a 3 hour period, it's going to do all that, or an annual hour period. It just creates this ginormous file and then does all the post-processing to determine what the 3 hour average is at each location, or the 24 hour average, whatever you ask the model to do, that's what it does. Okay, so.
Where does it get the wind direction from? Is that like let's say you measure for every hour of the year. So hour 1 would be January 1st at 1 a.m.
Correct.
So does it average the wind direction and temperature of hour 1 from the past 10 years, or how does where does that data come from?
Yeah, so for PSD modeling, it's 5 years worth of actual metadata. For most of the state-only modeling, they use a 1 year met set, and it's usually for a specific year. Like forever, it was 1987 or something like that for TCQ. They felt like with 8760 observations, you're going to kind of pick up pretty much all variations of wind speed and mixing height and all that kind of stuff that you were going to see. So, like I said, the PSD is like 5 years, usually fairly recent years worth of actual metadata, taken at an airport usually. And usually the closest airport for the surface observations and the closest available airport for upper air observations, where they send up the weather balloon and all that kind of stuff to get the temperature differential as the balloon goes up. So that tells them what the available mixing height is. And they measure solar radiation and all this kind of stuff is kind of sophisticated, but it goes through a MET preprocessor to fit into this model. But the short answer is they're actual observations, usually from an airport.
So 45,000 times the top run to get all the data for each hour output. Now, the last bullet there is each hourly model basically is independent of every other model. So it doesn't, some models will actually do this hour, then find out where the plume is, and then change the wind direction of the plume, and then change the wind direction of the plume, and change the wind direction of the plume, depending on what changes, how the wind migrates. This assumes that for the initial hours being permitted, that keeps steady for the entire dispersion of the plume, even if it would have taken
Right. So,
It doesn't move the plume around in fact, but it does give each hour from the point source perspective, we're committing this long for each hour for 5 years. So that's why it crunches a lot of numbers.
So if you're 60 miles from the nearest airport, it just does it for, like it were at that airport?
well, I'm not sure how other states work. TCQ, yeah, it's going to pick, they have pre-approved metadata sets, and they're just going to say, you know, for Houston, you're using Hobby Airport for 1987. That's it. And for Upper Air, you're using Lake Charles Upper Air. Now for West Texas, where you are, I mean, I don't know, they might say Abilene, or I'm not sure. Yeah. You know, maybe there's something in Big Lake or something that they use. You know, it's got to be quality airport kind of data that's gone through. But they pre-process it. TCQ pre-processes it, and basically you just get this data file. And when you're executing the model, you just tell it where to go to get the metadata, what file to look at to get all the metadata. So it'd be for every hour of the year.
In your experience, how have model results delayed or expedited project timelines?
They delay them, not expedite them. You know,
Even if it's a governor's project, they don't go very fast.
and no, it's gotten fairly sophisticated. The modeling process did, and when the NACs were higher than they are, when they were less stringent, it just wasn't a big deal. I mean, you put in your application and then you modeled the numbers in your application, and you passed usually. You know, and now with the new PM 2.5 24-hour NACs, and the new SO2 1-hour NACs, and the new NO2 1-hour NAC, these things are so much more stringent than they've ever been before. That more often than not, you're going to have to go through the kind of iterations that we're going to talk about in a few minutes to get these models to pass. It just doesn't fall out anymore. So the short answer is it almost always extends your timeline. The only good news here is that you're usually doing this modeling analysis on a parallel path of the review of the rest of your application. You're sending in a separate modeling report. It's going through your permit engineer, but it's going to the modelers at the state agency. They're the ones that are reviewing it. They're going to be coming up with their questions the same way maybe the permit engineer is coming up with their questions. You know, so you'll get, why did you use the surface roughness factor? We don't think that's right. It looks to us like it should be medium roughness. At the same time, where the permit engineer is saying, you know, this rundown tank temperature that you used in the calculations doesn't look right. So you're just getting all these NODs during essentially the same review practice. But
Texas is pretty generous as far as letting you submit this stuff after the rest of the application is being submitted. A lot of states require this to be completed and passing before you submit the application to begin with. So all the modeling's got to be
yeah,
done from.
I think Texas realizes there's going to be so much iteration that, you know, in the perfect world, you would agree on your BACT, you would agree on your calculation, and then you would put those calculations in the model. It rarely works like that anymore. I mean, you'll do that, but usually those emission rates may not be enough to get you to pass. There's still going to have to be some tweaking during the modeling process, at least for big expansions. Okay. Keep running through this. So they just, you know, I already said this. It just repeats this process for every emission point, for every receptor location, for every hour of the year. Okay. So how's it work? You put in all your stuff, you into the air mod model. You get your output. You're going to compare that to your quality standards. You're going to develop your source contribution, or what I'm calling culpability analysis. You know, all you're trying to do is identify where the troublemakers are. You're going to make some refinements to the data input for those troublemakers, and you're going to run the model again. You're going to tip everything upside down one more time, and eventually you're going to get to a passing model, we hope. And at that point, you'll develop your modeling report and all your graphics that show where your concentrations are and submit that to the agency. Okay. And when we talk about doing this, we're gonna do it on a two-tiered analysis. And the first tier, I mean, it's the same model and it's just as sophisticated, but the first step we're calling a screening analysis, and this is just modeling to proposed project only, right? And we're trying to get that, just your proposed project under your significant impact level. So these are what we were calling our project counting emissions from yesterday, just our project increases and decreases go into the SIL analysis. And if we can't get under the significant impact level, we go into an area of impact analysis that's modeling the rest of the plant, and usually all your neighbors too. Okay, so that's the first step, just your project. Think of it that way. The second step is NACS and PSD increment analysis that takes basically your significant impact area, the area you're over the sill, and adds 50 kilometers to that, and you're basically modeling everything in, let's say, a 55-kilometer radius. And if you're in a place like Houston, that's a lot of modeling. Okay, so you want to avoid that if you can. So if I can do this from here. Okay. So here's our modeling thresholds for, I mean, this is kind of a reference table to break it down by pollutant and averaging period. These are all the significant monitoring, modeling locations. This monitoring exemption is, theoretically, they could ask you to put a pre-construction monitor out for a year if they didn't have modeling data in the area, if you're over these monitoring exemption levels when you model. So the modeling is a real important part. You want to get under these levels for sure, because you could be stuck with up to a year of pre-construction monitoring if you can't model your project under these levels. And then we have the NACS analysis and an increment analysis, and these are all the standards that are set by EPA, and we just got to get over them. So, we explain all this to our Japanese CEO and just re-emphasize to him that the goal in all this is to get under the seals. If we do so, we're going to avoid modeling all the other existing site and this regional modeling. We're going to avoid the increment modeling and the next, and also a great deal of the modeling schedule delays. So we're going to make every effort to get under these seals with our project. Sure.
So is there any concrete guidance out there if I'm above the sill on my modeling? No ambient monitors are there, but I've got some nearby. Is it case by case to determine if I can get the state to accept that? If they're modeling, say I'm going to be over for particulate, but I've got a particulate monitor down the road at another facility. Can I use their ambient data to prove that I don't need to do the pre-construction monitoring?
My experience is they're really good about working with you to do that. Not that they're not going to put you through the ringer to demonstrate that monitor is representative of your area too. So here you go. You're going down the path, and hopefully it is right down the road, because you're gonna say the industrial area is very similar in terms of industrial density and the road surfaces, I mean, all the population generated emissions are going to be very similar, and yada 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 yada. In other words, we would basically get the same answers from this neighbor monitor we would get if we would monitor at our fence line or some other place close by. So they're going to make you jump through some hoops, but my feeling is at the end of the day, they're going to let you use that other monitoring data whenever possible. The key is finding the right pollutant at the monitoring station and just being able to make that argument. Okay. So that's it. See, here's our project location, and then we got a radius of impact, and these are all the predictions inside this crazy thing or over this sill, and so we're going to determine what our area of impact is just by drawing a circle around the bigger part of it. And then we're going to go out 50 more kilometers and get every industrial source in there and model them too, if we don't get under that sill. That's what we want to avoid doing, right? Okay, so when we do that, we're going to compare the model results to the NACs and to the increments. We do all that modeling, then we're going to add a representative background concentration. So we're doing a little double counting, right? Because we're modeling these sources, but we're also adding a background concentration that includes some contribution to the monitor. So it's jacked up, but that's kind of the way the first cut works. And the increments, remember the first day I said, you know, it wasn't only to enhance, but enhance and protect. And we talked about this idea of significant deterioration. That's what the increment is. So it's not only comparing everything plus a monitor background to the National Ambient Air Quality Standard, it's comparing all the sources that came into existence since the PSD rules came up and are eating up this increment, or this increment that EPA said you can only pollute up to this amount, right? So you're going to have to go through and sometimes the states have a good database, sometimes they don't, and figure out what sources in the area came online after the first PSD application and began chewing up this available increment. So it's a hard standard too. Sometimes it's tougher to pass than the National Ambient Air Quality Standard. But you model all those as a separate standalone analysis. And if you're over that increment, you don't get to do it. Okay. So in the last slide of your presentation, the CO, you explained that a detailed report is going to be submitted to the state. It's going to outline all of our inputs and assumptions, that we're going to do effect screening level for all our VOC compounds and everything else that we admit. It's going to be reviewed by the TC toxicologist, and they're going to eventually find that acceptable, and the permit review will proceed finally to the final public notice and the draft permit, right? And so you ask if there are any questions from Japan regarding the modeling analysis, and discover to your dismay that the phone is silent, and then the CEO's assistant informs you that the CEO stepped out some time ago for another call but wanted to leave these instructions. Proceed with the required TCQ modeling. Inform him immediately of any issues associated with schedule delays or additional control or capital expenses. And she also wants to remind you that the CEO clearly stated permit voidance or delay is not an option, right? I'm picking on the Japanese, but it could just as well be Germans. Same way. You will get the permit. There would be consequences. So you're beginning to wonder if you just completely bored the CEO to death. He wasn't even listening to half of
This
it.
hasn't been boring for you. It's just that whenever I start to talk about Elaine, I always get so carried away. I lose all track of time. Well, I could go on for hours, but I'd probably start to bore you. You know, I really couldn't blame Elaine. I wanted a career.
Okay. All right. So you're a little irritated, but at least this CEO briefing's over and you can get on with the task at hand. So you do a preliminary screening analysis, and which you're running the model exactly the way you turn in the permit application. It's got your emission rates, it's got all your stack release parameters. So you're just going to make the run just completely consistent with your application and just kind of see where you are. So you do that, and here's the way the results come back. you've got bad news. You passed on the CO 1 hour, just the way it was. You got a SIL at 2,000 and you only modeled at 934 micrograms per cubic meter. You're done. You're completely finished with the CO 1 hour. The bad news is everything else, it's just crazy bad. You know, you're 29 times the PM10 and you're 15 times the PM 2.5. More than that, 29 times the PM 2.5 as well. Nothing looks good. Okay, you passed the 3-hour sulfur dioxide and the annual sulfur dioxide, but you got some work to do. This is not good. So what do? You take these pollutant by pollutant, source by source, and just begin to see where your problems are and fix them. You know, you just look for your culprits and just kind of peel back the onion until you get to where you are. So let's start with CO, the 8-hour culpability, right? Because we're just going to kind of go through here. We were only 1.6 times. We need to get this 805 down to about 500. So let's look at where we are by seeing what we put in the model and then kind of focus on where we need to go with the sources. And this is just kind of dealing with culprits. And probably the best person that ever dealt with culprits was Dirty Harry. He knew how to deal with a problem. Okay. So here's what we're getting. We're getting this crazy chart that's got all of our different emission sources on it and our predicted concentrations and various things. And here's our location, our height, and our temperature, and all that kind of stuff. And we're looking at all these things for each averaging period. We want the 8-hour average. That's what we're concerned about. That's the one that didn't pass. And here's all our stack parameters. And here's our emission rate in pound per hour. So which ones really caused the problem? We got this long list of sources that we modeled for CO. Which ones caused the problem? We're able to develop this culpability analysis by looking at each one of these individual sources. Remember I told you we had this big file, and for every hour, for every source, it told you what. Well, so we've asked the model to tell us what the source contributions were at the maximum locations. And this is the way it kind of fell out. All the sources were that 805, they were trying to get down to 500, right? But when we looked at the cracking furnaces, them alone were 453. So we know that something's got to give on the cracking furnaces. And these decoking vents were also really high. Flare and engines and other sources kind of fell off, but man, here's our target. We got to get below 500. So let's drill down on the assumptions that we used in the model that predicted these high cracking and decoking furnace concentrations. So we go back to the design team and we talk about how the calculations were done, and we realized that when we modeled it right off our emission rate table. In Texas, that would be our table 1A, right? And we modeled all our routine and maintenance activities as if they occurred simultaneously. It's the most conservative approach, and that's was good for our first cut. But now we've got to go in and figure out, are these things really happening simultaneously? Are we really doing maintenance on the furnace at the same time the furnace is running full blast? Which one's the most conservative emission assumption? And what we determined was that stack parameters, that they're not going to indeed occur at the same time. And the stack parameters aren't going to vary significantly between routine and maintenance operations. And the permit team said, you know, if you guys really need it, and we could probably go up on the stack height just a little bit. We don't want to go up too much. It gets real costly over 200 feet, but we can go up a little bit. So then we looked at the decoking activities and determined that really there's 4 of these decoking stacks, but only 2 of them could possibly operate in any given hour, be in decoke mode. And probably only 1, but for sure no more than 2 are ever going to operate during the same hour. And if you guys need to, we can go up on the stack heights on those a little bit too. So we put in, this is just kind of showing you the routine operations and then the MSS operation. You can see they're really high on MSS. So we determined that it's only MSS is going to be driving the worst case hour from this. So then we did some modeling adjustments for the decoking vents, operating only 2 of these vents simultaneously. So we need to figure out, well, what 2 vents are those? So we determined which ones are the worst 2 decoke vents. And, you know, they're almost the same because they're almost in the same location. But we finally decided that, you know, this decoke 12 and 34 vent were going to be the worst case. Let's model them only. Let's take our stack height up. Let's take our decoking stack height up. They said it'd be fine. And then let's just remodel this thing again, see what we did. So when we did the investigation, we isolated the cracking furnace and decoking activities as the troublemakers and determined they wouldn't happen at the same time. So we used just the worst case MSS emission rates. And then we threw out 2 of the 4 decoking operations because they couldn't occur during the same time. We raised the stack heights, and then we reran the model for all the pollutants, right? So lo and behold, we did a great thing, and now we're way under for CO. And we also, when we did these iterations, we also got the annual NO2 to drop down below the seal of 1 at 0.9. So we worked out of that to seem like nothing else changed. So, but anyway, we got our CO problem fixed, and
But that means they're going to have to go in and increase their stack height, right?
yeah,
Okay.
yep, that's what it means. That's what it means. And they're probably also going to get a permit condition that says thou shalt not decoke more than 2 decoking furnaces during the same hour, or during the same 8 hours in this case.
Try to live within what you actually do first, and then put restrictions there as palatable.
Yeah. So you bring up a really good point, though. You don't want your modelers just doing this stuff. You want them talking to the design team, and the design team's got to say, it's okay. You know, we can live with that call stack. This is an important project.
Something that you can easily track.
Yeah.
It's not hard to track.
Yeah. Yeah, that's right, Ginger. I think that's a good statement, too. So,
Stack an extra 2 feet, that's easy to track. It's done, it's done.
yeah,
Well, but 2 and 2 at the same, you know what I mean?
Right,
2 and
yeah,
2 at the
2
same time, or filling the tank, you know, whatever it is.
right. That's right.
Yeah, if it gets too complicated a scheme, then it's hard to comply with it.
And if you just let these dispersion modelers run, they're going to come up with kooky stuff that makes the model pass, but your operators are going to go, man, that's crazy. We don't want to do that. We don't want to have to track that. So all the communication is just important, and that's something that unless you as a permit manager gets involved, these modelers and these designers aren't going to talk very well together. So let's just keep going. We're going to move on to NO2 now, and you know the standard is NO2. Most of the emissions were in NOx, right? They were in NOx. So we do this default ambient ratio method that says, you know, this amount of the NOx is really NO2. They let us jack that down 75% for the annual period and 80% for the hourly period. So we make those adjustments to the NOx, and then we run our culpability analysis. And this is grim. We're trying to get to 7.5 micrograms per cubic meter. Remember I told you how tough that seal was in the standard. We're at 112. So we're still, you know, we're more than an order of magnitude off still. And the cracking furnaces alone, as well as the flare, as well as the engines, as well as the other miscellaneous sources, you know, they're all over the 7.5. So we're gonna have to do something on all of these things, right? We're gonna have to fix all of these. So we, you know, again, we just go in and start peeling back the onion, take them on one at a time. And what usually happens, at least in Texas, is the same thing. This routine and maintenance activities aren't going to be occurring during the same hour. And this is what makes you talk to your operations more than even your permit application. It's figuring out which of these things can happen simultaneously and what is our worst case modeling hour in this case, because we're talking about NO2. So the same thing, we ferreted it all out, and we determined that the emission rate during maintenance activities wouldn't exceed the daily routine operations. These are mainly furnaces. We're talking about the cracking furnaces now. So when these things are up running full tilt boogie, they're actually making more NOx, or NO2 in this case, than when maintenance is being performed. And we verified that through the operations. So now we know that we don't have to include maintenance activities. If we just ran them in routine mode, that's going to be our worst case hour. Right.
And have you measured 2.5 on these cracking furnaces?
Yeah, we're going to get to 2.5 in a minute. Just hold that thought, because it's a great thought. And I got a video for you, Tammy, at the end of the day. 2.5 is nutty. So I got something you'll appreciate later. But right now we haven't got to 2.5 yet. We're still going through NOx. Okay. And here's all these other sources, the flares, engines, tank. These are the biggest troublemakers, but these don't operate continuously, right? We're doing flaring mainly for MSS operations. Engines, we're just testing them once an hour just to make sure they're emergency engines. So we go by and test them for an hour every week. We take down our tanks and do cleaning and stuff like that, sometimes only once every 10 years. These things aren't going continuously, and so it's not realistic that they're going to contribute to exceedance of the NAAQS in any one given hour, right? And EPA recognized this when they came out with these NO2, the new NO2 NAAQS, and it's based on a 99 percentile. It's a 98 percentile basis. SO2 is 99, which basically means you can throw out 2% of the days, and they don't contribute to a violation of the NAAQS. Well, these things don't even operate sometimes 2 days out of the year continuously. And it's not likely they're going to affect the statistical average. It's not the highest first high. It's like in this case, like it works out to be like the 7th highest day of the year at the 98%, 2% of 365. So EPA recognized this, and they came out with what they called an intermittent source policy for modeling NO2 and SO2. And basically it said if you can demonstrate that they're not statistically going to contribute to a violation of this 98% standard, you either one, don't have to model them, or two, you can just tell us how many hours a year they do operate, and we'll let you annualize that emission rate and model that. So like for these engines that are modeled so terrible, but we only test them for an hour a week, they only run for maybe 52 hours of the year. So we would take that emission rate, multiply it by 52, and then divide it by 8760, and they're saying model that number, which is a small fraction of the number that we had before. So we're using this intermittent EPA policy to manage all these troublemaker sources that don't operate continuously.
Does it say, is the policy specific to anything, or you can use it for anything that's intermittent?
You can use it for anything that's intermittent with regard to NO2 and SO2. Did they extend it to PM 2.5? no. Why? I have no idea. But they didn't. They didn't. Now, perhaps it's because PM 2.5 has a 24-hour averaging period rather than one averaging period. So if you were running one of these engines for PM 2.5 and it was only 1 hour of the year, you could divide that emission rate by 24 when you model it, right?
Is there any conditions on how the sources have to be permitted? I mean, do they have to be permitted a certain way? Like if you had groups of equipment like engines permitted as a source, and let's say you had 100 welding machines, or light plants or whatever, and they're permitted as a group, a source, and do they have, you know what I'm saying? Does that make sense? Do things have to be permitted in a certain way in your Title V in order to use the intermittent status rules?
I don't think so. I think they just, and this paper's in your, these papers are in your jump drive, and it's called the Tyler Fox intermittent EPA policy. And when EPA wrote that paper, they give some examples. And one of the examples are engines that operate less than 500 hours a year. And they talk about some of these different things. But so I get the feeling that it's not so much the way you permit them, but how many hours per year they operate.
Let's say you have a heater, and you have the regular normal operation emissions, or FCC, that's a better one. You have normal operation emissions, but you also have a separate startup emission rate that's all lumped together. Can you break out that startup emissions because you have hives, CO, and other things? Can you do the startup emissions, break those emissions out of the total and permit that as the intermittent, even though it's all one source? Does that make sense?
Yeah, it does. It does to me. I mean, it's not much different than these furnaces. And I think the short answer is yes, but probably the way your situation would come down is you would see what the cat cracker NOx emissions were during routine operations. And, I'm not sure on what kind of maintenance you'd be doing, but my guess is when you did that, even if...
Installing a heater, when you install a coker heater, you have really
Yep.
high, so same principle.
It is the same principle. So imagine when you're doing that, the first determination would be, are those routine emissions higher on any given hour, or your maintenance emissions higher in any given hour? And if the maintenance emissions were higher than the routine, I mean, you're not going to be doing both at once, right? So if your routine emissions are higher, that's your worst case, without any doubt. If your maintenance emissions turned out to be higher, I would ask myself, how many hours a year do I do these maintenance emissions? And can I make these maintenance emissions qualify under this intermittent EPA policy? And if I can't throw them out altogether, are the hours certainly less than 500, maybe less than 120 or so, but however many hours it is, can I make it fit under my intermittent policy and annualize those? And then are they less than my routine emissions? And then I'd flop all the way back and say, you know what, I've determined that my routine emissions are my worst case hour. And that's all I'm going to model. That make sense? Okay. All right, so I've kind of talked about these statistical standards. There's a 98th percentile for NO2. There is a 98th percentile average over 3 years for PM 2.5, and there is a 99th percentile. It's a percentile of the 1 hour daily maximum, and this also average over a 3-year period for SO2. Don't know why they didn't include this in their intermittent policy, but they didn't. I suspect it's because it's a 24-hour average rather than a 1 hour average, and they thought, it had a higher percentage of affecting any given day. because of averaging period. So I'm not going to go into much more detail in that, but you can read about it in these slides. And this is the intermittent policy. So this is the paper. All these are in your jump drives. Like I said, it applies to SO2 as well. Does not apply to PM 2.5. So, you know, at the end of the day, we looked at all these engines and tank control policies and decided all this intermittent policy fit well with these sources. So we went back to TCQ and we said, let's just say that we said, hey, we don't think we ought to model these tanks at all, and really, I don't think we should model these other things. And they said, well, we think you should model them, but we're going to let you annualize emissions. So we threw all that stuff back into the model, and with annualized emission rates, we looked at our stack heights, because we'd already raised our stack heights for NO2 and all that kind of stuff. We updated everything. Here's the same 500 hours that's mentioned in the paper. You know, when you claim that, when you say, you know, we're only going to do this for 120 hours or 500 hours, expect that to show up in your permit conditions. You know, it's sad but true, but that's just going to be one more thing you track. Okay, it's going to show up. So we did all that. We adjusted our hourly emissions, and then we ran it again. And looky here, we're still over on the hourly, but we're not over like 20,000 times or something. We're only a little over 2 times the short-term standard. We're at 15.77 instead of 7.5 when we made those adjustments. So we made a tremendous leap. We went from 15 times to 2 times the seal, but we're still over the seal. So we do our analysis again, and it's still these cracking furnaces. They're big, and we've got to find a way to cut them in half again. So we meet with the design team again, and they the management wants to rule out any kind of modeling solution to this problem. Do we really have to get under the sill? Can we look at the ozone limiting method, which is another, or this plume volume molar ratio? These are modeling considerations that might alter your NO2 to NOx ratios in any given stack if you got data. And they're saying, can we use other MET data? Can we use site-specific MET data? And maybe if none of this stuff works, is it going to be so bad if we don't pass the seal? What would happen if we modeled the rest of the facility? How would that look? Maybe we can just pass the NACs and increment. So we run through all those kind of investigations, and our first one was our, jacking with our NOx, NO2 to NOx ratio, and we did some sophisticated modeling tricks to do all that, and we maybe even got some in-stack testing for NO2 to NOx ratios, and we ran them all again. So we looked at this ozone limiting method and this plume volume molar ratio method, and it didn't help at all. Didn't help at all. We ran it again. It didn't help at all. Our NO2 concentrations actually went up a little bit, from 15.77 to 17.6, and it's because it was because we were in a NOx limiting atmospheric condition. The NOx was driving the ozone formation process. That was a step limiting factor rather than the VOCs. So it just didn't work for us. So that didn't work. So then we went to site-specific MET data and pre-processed some site-specific MET data instead of using the TCQ or EPA, and reran everything again, and guess what? That didn't help either. It actually made things worse again. We went from 2.1 times to 2.6 times. And at this point, my modelers were getting pretty depressed. And my movie quote is, dealing with your modeler after disappointing results. Are you crying? There's no crying. There's no crying in baseball. Tom Hanks. Yeah, okay, you got it. Very good. So then we said, okay, what if we didn't get under the seal? Is this going to be so bad? Let's check it out. So we did area-wide refined modeling, and we threw in Rising Sun's existing unit, this new big expansion unit, and all the other industrial sources within 50 kilometers. And went through our database retrieval and added an NO2 background from a representative monitor and looked at the receptors which were over the seal, and here's what we got. The proposed project, again, this was a 15.7 number. We were trying to get down to 7, so that stayed the same. And that was only 8% of the NACs, but then if you add this background concentration, which is 94 to it, you know, that jacked it up. So we did the existing ethylene unit, and look, because of the bad NOx control of their heaters and furnaces, wow. Our other older sources alone ate our lunch. They were already at 95% of the NACs, and if we added a background, we were over the NAC. So that told us right then, these other industrial sources, because they were further away, they didn't affect us so much. It was only 8%. But this value alone said, you know, it's not doable. We're not going to pass the NACs. We're going to end up submitting this data to TCEQ, and they're going to say, well, if you want to pass, you've got to control some of your existing sources. You know, your existing cracking furnaces or something. These older ones, replace them, get some control on them. So we were able to go back to them and say, basically, these things weren't working. And at this point, I was really worried about my modelers. We tried everything. In fact, some of them started slipping into some bad habits, old bad habits.
It's like I picked the wrong week to quit smoking.
You know, that didn't help. Adjusting the NOx ratio stuff didn't help.
It's like I picked the wrong week to quit drinking.
And I could see these guys are just falling apart at this point. And then we did the site-specific metadata, and it didn't help.
It's like I picked the wrong week to quit amphetamines.
Worried about them a lot. Then we did the site-wide NACs, and that analysis is hopeless because of our existing sources.
It's like I picked the wrong week to quit sniffing glue.
So, you know, we're looking for some inspiration because really for the first time we're thinking this is over. We don't know what else to do. So, of course, we turned to, who else? To John Belushi for our inspiration.
What? Over? Did you say over? Nothing is over until we decide it is. Was it over when the Germans bombed Pearl Harbor? Hell no! German? Legality's rolling.
And then we looked at Yoda. John Belushi and Yoda said, do or do not. There's no try. Regained our inspiration, met with the modeling, with the design team one more time, and finally determined that we might be able to make this whole emission cap rate feasible. In other words, instead of looking at these furnaces on an individual pound per hour basis, if we could average the emission rate and commit to a total pound per hour emission rate out of our furnace block, that would give us a tremendous mathematical advantage because these things are going to swing a little bit here and there, and we wouldn't have to hit any individual limit, but as long as we made the total mass limit for the whole furnace block work. So they said, you know, just tell us what that is and we'll tell you if we can get there or not. So we modeled backwards to a place where we could get to that 7.5, and it turned out that you know, that was our plan forward. Let's just figure out what that number is, take it back to the modeling, to the design team and say, can you guys get there on a block average determination? And we did all that, and we just kind of iterated the model back and forth till we hit the seal. If the impacts are greater than the seal, we modeled with a lower emission rate. If they were lower than the seal remodel with the highest emission rate until we hit exactly the seal. And we determined what our worst case furnace was and assumed everything was coming from there just to find out this mass emission rate. And it turns out it was 54 pounds per hour. That's just what the number was. When we modeled this worst case furnace at 54 pounds an hour, we were at 7.5 and we hit the seal. So then we take that back to the team, and after considerable evaluation, they determined that they could operate. It provided them with enough flexibility if that was averaged over the entire furnace block. And since that was lower than the previously approved BACT, TCEQ said, yeah, fine. You guys want to agree to 54 pounds per hour and just have one limit in your maximum allowable emission rate table? That's fine. That's your short-term limit. It's for the whole block. So we did that, modeled it again, and guess what? We turned out at 99.4%. So cutting it close. There's no headspace here, but you know that TCEQ understood that we modeled backwards to get to that number, and it was a low number. So that was it for NO2. So here the NO2 was by far the greatest saga. We might skip a few of the other pollutants, but what did we learn in these? What didn't work was the alternative NO2 to NOx ratios. It made things actually worse. The alternative MET didn't improve results. Going to a refined model with a full NACS evaluations was unworkable because of our existing furnaces. What did work was taking use of this intermittent EPA policy. That was the biggest step forward to improving our results, and that coupled with the idea that we could manage our emissions to a single block furnace cap was what kind of put us over the top. Okay, so moving on to particulates matter, we got a few more minutes before lunch. I'll get into a little bit of this. We're just doing the same thing. We're looking for the culprits, and we're just going to peel back the onion until we get there. And this is the way you have to do it on these modeling analysis. What happened?
Round up the usual suspects.
So what are our usual suspects? Well, we know them by now. They're the cracking furnaces and the decoking vents, right? So we're going to run through the same thing here. All these little things were couplable sources, but when we applied that 24-hour average, because this is a 24-hour standard, right, for PM210. So when we adjusted those emission rates from a pound per hour rate to a pound per 24-hour rate and remodeled, basically we got there. Okay? And so PM 2.5 was our next one. And I'm wondering if we should hold that one to after lunch, Bruce. Because of the things you talked about, it's a little stickier and you don't get through 2.5 just a little. But we're almost there. You can see that this table is looking a whole lot better than our previous just modeling of everything in our permit. For 2.5, we need to get that down by almost a half. But this one's really within striking distance, the SO2, and this one's just tiny bit over as well.